universe is marvelous. Just look at the sky. Huge planets, bright stars, vast galaxies, massive clusters. It just fills us with tremendous amazement. In the last century, our exploration of the cosmos has reached unprecedented depths. From the first echoes of the Big Bang to the accelerating expansion of space, from dark matter and dark energy to ripples in space-time itself. Yet, with every answer, deeper questions have arisen. How far are we in understanding our universe? What lies at its beginning? Are there limits to knowledge, observation, and even comprehension? Is the astonishing order of the cosmos merely accidental? Or does its beauty, fine-tuning, and mathematical elegance point toward a deeper intelligence and purpose, as some of the greatest scientific minds have reflected across generations? To explore these profound questions, Bhaktivedanta Institute invites you to an extraordinary voyage through our cosmos, where some of the world's most brilliant scientific minds will share their insights and discoveries, including Andrei D. Linde from Stanford University, John H. Schwartz, theoretical physicist, Caltech, USA, Wendy L. Friedman from the University of Chicago, Ofer Lahav from University College London, Avi Loeb, Harvard University, USA, Pankaj S. Joshi, International Center for Space and Cosmology, India, and many more leading thinkers from across the globe. This is a space for rigorous science, open inquiry, and meaningful dialogue, where curiosity meets humility. Welcome back to your own astonishing home, the universe.
Good evening, everyone, and a warm welcome to all our guests, dignitaries, speakers, faculty members, and all our participants for joining us today from across the country and abroad for the Golden Jubilee Lectures on the Voyage to the Cosmos: History, Models, Theories, Latest Images, and Foundational Issues in Understanding the Universe. My name is Ritvik Galam, and it's my privilege to be your host for today's program. Today is day 2 of the lecture series, which began on the 16th of March, Monday, and will continue till the 22nd of March, Sunday, in online mode, bringing together distinguished scientists, scholars, and brilliant thinkers around the world. The timings of the lectures will be 5 p.m. to 8 p.m. from Monday to Friday, and 10 a.m. to 1 p.m. on Saturday and Sunday in Indian Standard Time. This lecture series is organized by the Bhaktivedanta Institute, Kolkata, as a part of its Golden Jubilee celebration, marking 50 years of dedicated service to the humanity. Before we move to today's schedule, I will briefly go through today's schedule. The first talk will be delivered by Professor Paul J. Steinhardt from the Department of Physics at Princeton University, USA. He will speak on the fascinating topic, Time to Take the Big Bang Out of the Big Bang Theory. The second talk will be delivered by Professor Pankaj S. Joshi from the International Center for Space and Cosmology, Ahmedabad University, India, and he was a former senior professor at Tata Institute of Fundamental Research, Mumbai. He will speak on a very intriguing topic, the story of black hole, life and death of massive stars in the universe. The third talk will be delivered by Professor Andrei Linde of Stanford University, USA. He will speak on the fascinating topic, universe or multiverse. Before we proceed further, I would like to request all the participants to please scan the QR code displayed on the screen to submit your question to the speakers anytime during or after the lecture. You may take a screenshot or a photo of the QR code. Alternatively, the Google Form link has been shared in the chat box. It's my great privilege to introduce our distinguished speaker, Professor Paul. Professor Paul J. Steinhardt is an Albert Einstein Professor in Science at Princeton University and a visionary theoretical physicist who has fundamentally reshaped two distinct fields of science, cosmology and condensed matter physics. As one of the original architects of new creation, he helped establish the standard model of the early universe and later proposed the revolutionary bouncing model of cosmology. This bold paradigm posits that the universe undergoes eternal cycles of expansion and contraction driven by the brane collision in higher dimensions, offering a mathematically consistent alternative to the Big Bang that resolves the predictive paradoxes of the multiverse. Steinhardt is equally renowned for redefining the concept of the matter through his discovery of quasi-crystals, ordered materials with forbidden symmetries previously thought impossible by the laws of crystallography. His scientific tenacity led him to organize a daring expedition to the Russian tundra, which he proved the natural existence of these exotic structures in ancient meteorites. A recipient of Dirac Medal and the Oliver E. Buckley Prize, Steinhardt's work stands as a testament to scientific rigor, bridging the gap between the abstract geometry of the cosmos and the tangible atomic structure of the solids. With this, I would like to invite Professor Paul to begin his lecture.
Thank you. You able to see my slide?
No, sir.
Can you see it? No. Okay,
No.
one sec. What happened to the share option? 1 second. Sorry. Let me first off on the video. Let me put on the share. Let me put on this. Let me share that. And
Yes, sir. Now we can see. Can you please make full screen?
I'm going to try to make it full screen now. 1 second. View. Does that work?
Can you please click continue to share? Yeah, yes,
It's
that's perfect. Yes, that's right.
okay.
Yes,
Okay,
yes.
very good. Thank you. Well, thank you for having me this evening, and I appreciate the opportunity to participate in this voyage through the cosmos. So, the title of my talk today suggests that it's time to take the Big Bang out of the Big Bang theory. The first thing that many of you might be asking yourself is, how is this possible? Isn't there an overwhelming amount of evidence for the Big Bang theory? The answer is yes and no. And the reason is because there's really two ideas involved in the Big Bang theory. One of the ideas is that the universe was once hotter and denser than it is today, and that it's been expanding and cooling and spreading out over the last 13.8 billion years. For that idea, there really is an overwhelming amount of astrophysical evidence, and one doesn't really want to fool around with that story given all that evidence. But the second idea of the Big Bang Theory is that the universe sprang from nothing, began from nothing, had a definite beginning 13.8 billion years ago in what we call the Big Bang. And for that, there is no evidence, not a shred of evidence, because to get to that idea, you have to extrapolate equations back in time by more than 70 orders of magnitude in density beyond what we can test, either in the cosmos or in the laboratory. So if there's not a shred of evidence for it, it's perfectly reasonable to question whether or not it's time to take the Big Bang out of the Big Bang theory. But why? Why should we be doing that? Well, the problem is that if you introduce the Big Bang, it creates a series of problems. The first is the Big Bang itself is a singularity of the equations that we're extrapolating backwards in time. A singularity means a mathematical pathology, a sickness. We extrapolate the equations back and we find that certain moment in time, 13.8 billion years ago, the equations tell us temperatures and densities became unphysically large, infinite. That's impossible. That's an idea that needs to be replaced. So normally when we encounter singularities in solving equations of physics, what that usually means is your theory needs an improvement. You're not supposed to take the singularities seriously. The second problem that it creates is a tremendous amount of disorder. This is an artist's conception of what a Big Bang might be like. After the Big Bang, the universe immediately passes through a period in which quantum gravity effects become large. And anything that couples to gravity, anything that's connected by gravity, which is everything, matter, radiation, and space-time itself, is going to undergo huge fluctuations, huge variations across space, creating a lot of disorder or entropy in the universe. In fact, bringing the entropy to the maximum, close to the maximum that's possibly allowed in the universe. But the entropy in the universe today is much less than that entropy. So the puzzle is, how do we go from the large entropy coming out of the Big Bang to the modest entropy we have in the universe today? That would seem to require violating the second law of thermodynamics. And then this entropy takes the form of disordering everything. It makes for a chaotic universe with chaotic inhomogeneity, anisotropy, and curvature variations, as this artist is trying to convey. And that looks nothing like the universe we observe, the early universe we observe. For example, when we look at the last scattering surface from which the cosmic microwave background radiation emanates, and from which we obtain an image of what the distribution of matter was at that time. It shows a very homogeneous, isotropic, flat universe with modest entropy. Well, we've known about these problems of the Big Bang for many decades, and this was what motivated the idea of putting a patch in the theory, in the Big Bang theory, the patch that we call inflation. A patch that we place between the Big Bang and, say, the microwave background, the last scattering surface when the microwave background is emitted, to try to correct the problems created by the Big Bang. But what we've learned over the decades since inflation was introduced in the 1980s is that inflation does not help. First of all, it doesn't eliminate the singularity. If some of you have been reading articles or magazines lately, popular magazines, this statement may confuse you because some in the inflation community have decided to rename or redefine what a Big Bang means. Instead of what they propose is to use the word Big Bang not for the beginning, but for when the universe first reheats after inflation. If you use the term Big Bang in this new way to represent the universe after reheating, that's not a singularity. But by relabeling things that way, it hides the fact that if you go before the reheating and you go before inflation and you extrapolate back in time, once again you end up at a singularity. This theory still has the singularity. It's just sitting there behind the inflationary period. So inflation doesn't help get rid of the singularity problem. Furthermore, inflation makes the entropy problem exponentially worse than it was in the original Big Bang theory. I said that the problem of entropy is that coming out of the Big Bang, we should get an entropy which is much bigger than the entropy we have today, which is a problem. But inflation requires an exponentially smaller entropy to get started. So it exacerbates the problem, it makes it much worse. We have to, within a fraction of a second, go from come out of the singularity, create this tremendous entropy, and reduce it by an exponential factor, something like 10 to the Google power, 10 to the 10 to the 100th power, in order for inflation to start. And we have no mechanism for doing that. Thirdly, although it was supposed to solve the homogeneity, isotropy, and flatness problems, as we'll talk about today, it really doesn't. And I should point out that these conclusions don't depend on the particular shape of the inflaton potential, if you're familiar with that idea. It doesn't depend upon whether it's power law inflation, plateau inflation, or multi-field models. They all have these same diseases. And then there's the specter of the multiverse that makes matters much worse. Because in the multiverse, all things are possible. And our particular universe is therefore improbable because there are many other possibilities that can emerge in a multiverse, and they all do, every single one of them, and for an infinite number of times. At this point, some try to bring in the idea of anthropic reasoning to help sort out the problem of unpredictability of the multiverse. But that doesn't help because although the anthropic reasoning would eliminate possibilities which are inconsistent with our existence, it still leaves an infinite continuum of possibilities which are consistent with our existence, but which are not like us. And furthermore, anthropic reasoning takes us beyond the boundary of scientific reasoning, so that's another reason why I don't tend to recommend it. And then finally, contrary to common claims you might find in the literature, inflation is probably incompatible with quantum gravity. Well, what can we do about this? Well, how about replacing the Big Bang, jettisoning it from the Big Bang theory, and replacing it with a bounce? And by a bounce, I mean a smooth transition, a smooth non-singular transition from a period of contraction to a period of expansion. And by smooth, I mean we do not go through a crunch, we do not go through a phase of quantum gravity generation. This is a smooth transition, non-singular transition governed by predictable equations. In such a situation, you solve the singularity problem because you never have a situation where the temperature and density become infinite. You truly solve the problem. Secondly, you solve the entropy problem because you don't produce the large entropy of going through a phase where quantum gravity dominates. You have no such phase. You solve the homogeneity, isotropy, and flatness problem through a novel mechanism that I will be describing, something that's curiously different from what we imagined in the case of inflation. You avoid the multiverse because the multiverse is a product of having inflation plus quantum mechanics. Well, we have quantum mechanics, but we don't have inflation. So no multiverse, no uncertainty, no infinity of possibilities produced in the bouncing model. There's one possibility, and it's one that agrees with the universe that we observe. There are so-called geodesic incompleteness theorems, theorems like those originally introduced by Hawking and Penrose, which are sometimes these days called no-bounce theorems. But the kinds of bouncing models I'm talking about evade those theorems. Another interesting byproduct of bouncing models is they do not predict what are called primordial tensor modes, which produce a polarization pattern in the cosmic microwave background called B modes. And the reason why that's important, that it does not predict them, is that we don't see them so far. And then finally, this is compatible with string theory and quantum gravity. So many of the problems we saw for the inflationary outcome, Big Bang inflationary idea, are circumvented once you introduce the bounce. Now, as you might guess from this list, this is a huge topic. I can't discuss all this topic in 45 minutes. So I'm going to focus on just one of them, which I think is the most important challenge for any cosmological theory that you might imagine. And that's to explain what we observe from our mapping of the temperature variations across the sky, across what we call the last scattering surface, based on measurements of the cosmic microwave background radiation. So this is a surface which is a surface in space-time which is beyond the galaxies and taking us back in time about 13.8 billion years. And it shows an image which shows the variation in temperature across that surface. It's false color. So they're showing regions which are hotter or cooler than average. But it's important for this discussion today to keep in mind that these variations in temperature are extremely tiny. 1 part in 10 to the fourth, or 1 part in 10 to the fifth, or even smaller in some places in the sky. So if we just change the resolution a little bit, what we observe is something really amazing, which is across the last scattering surface, across the universe at that time, we were in a state of low entropy, homogeneous, extremely isotropic, the same in all directions, the same in every place across the map, spatially flat. And these are all conditions that need an explanation because they're not what you'd expect coming out of a Big Bang. So we're going to be talking today about 2 ideas that are designed to try to solve this puzzle of how we get from the Big Bang to the remarkably homogeneous and smooth universe we observe in the microwave background. One will be the idea of inflation following a Big Bang, and the other will be the idea of slow contraction followed by a bounce. Both of them have things in common, which I'll name first, and then we'll talk about the differences. So both of them are described by Einstein's theory of general relativity, which in the case of a smooth universe reduces to the simple equation I'm showing in blue on this slide. It's known as the Friedmann equation. H here represents what we call the Hubble parameter, which measures the rate of expansion of the universe. And the terms on the right represent contributions that will, through gravity, affect that expansion rate. The first term would be the term which describes the energy density, which is going to be causing the smoothing, which would be the energy that's driving inflation or the energy that's driving slow contraction. The second term is the term that describes the curvature of the universe, how curved space is. And the third term is what describes how anisotropic the universe is. That is to say, how different it might be in different directions. The goal of inflation and slow contraction, in either case, is to make sure that the energy density, the first term, becomes large compared to the other two terms, so that the other two terms have a negligible effect on the expansion of the universe, consistent with what we observe in the cosmic microwave background. And they both adopt a strategy of making sure that that first term becomes large compared to the other two. Each of these quantities depends on A, which is the scale factor, which describes the expansion or contraction of the universe. So A grows if you're expanding, shrinks if you're contracting. And all of them have in the case of expansion, all of them have the property that as A grows, if you're expanding, as A grows, all of them are decreasing. But they're decreasing with different powers of the scale factor. So they're decreasing at different rates. In the case of inflation, in an expanding universe, in the case of inflation, when A is growing, we want the first term to decrease, but decrease more slowly than the other two. For that, it's sufficient if epsilon, which is the quantity in the exponent there, is less than 1. Epsilon represents what we call the equation of state. It depends on the ratio of the pressure to the energy density of the energy that's driving, in this case, inflation. So we want to make sure that epsilon is less than 1, because then, although the energy density decreases, it decreases at a power which is less than that for the scalar curvature and less than that for the anisotropy. So over time, for sufficient expansion, the curvature and anisotropy become irrelevant. For slow contraction, there's a similar strategy. However, now the scale factor is decreasing because the universe is contracting during slow contraction. Once again, we want the first term to become larger than the second and third terms. This time, because A is decreasing, all the terms are growing instead of shrinking. As the universe contracts, the energy density, the curvature, and the anisotropy all grow, but they grow at different rates. And if epsilon is greater than 3, in this case, then the energy density, the first term, the energy density that's driving slow contraction grows faster than the second and third terms. So once again, we get a condition where we suppress the curvature and the anisotropy. Now, how do we actually get this epsilon? Well, that depends on the form of energy which is driving the inflation or slow contraction. And here again, the two ideas have a lot in common. They both rely on, in the simplest cases, they both rely on a theory which contains a mixture of gravity, the first term in the action in the top line, a scalar field, which has a kinetic energy, which is the second term, and it also has a potential energy, which is the third term. Because they share the same action, they satisfy the same equation of motion, which describes how the field changes with time. And that's the equation in red below. The difference in the two theories is, number one, in the case of inflation, the universe is expanding, which means that the Hubble parameter, which describes the expansion, is positive. And the middle term in that red equation acts like a kind of friction term for the field, transferring energy from the field into gravitational energy. In the case of slow contraction, the universe is contracting, so H has the opposite sign, a negative sign. So instead of acting like a form of friction, it acts as a form of anti-friction on the field. It converts gravitational energy into pushing the field ever faster. And that energy buildup ends up turning into the matter and radiation after the bounce that forms the matter and radiation we see in the universe today. The second way they differ from one another is the particular details about the potential. In the case of inflation, we want to have a potential which is large and positive during the period of inflation. That's because we want epsilon to be less than 1. And epsilon for a scalar field is given in that equation in blue. It's the ratio of 3 times the kinetic energy over the total energy. So kinetic over kinetic plus potential. If we want to make epsilon less than 1, we're interested in making the kinetic energy small. The smaller the kinetic energy, or the slower the field is changing its value, the smaller epsilon is. So for example, in this particular example, and there are many examples of potentials of different shapes which are possible, but in this particular example, what we want is the field in somewhere, let's say on this plateau, where it's changing because the potential energy is very flat, the field changes very, very slowly. And so if it starts at rest, it will change very, very slowly. That'll produce the condition we want of small kinetic energy compared to potential. That'll produce the condition of epsilon less than 1. And if epsilon is less than 1, the scale factor grows as a power of time that goes with the power 1 over epsilon. So it grows with a very large power of time, which is what we mean by accelerated expansion. Okay, how do we get contraction? Well, if we have a universe which is slow contraction, I mean, if we have a universe which is contracting, one also can use a scalar field and a potential, but in this case, the condition we want is different. We want to have epsilon large, not epsilon small. But that's easy to accomplish. All you need is for the potential to be negative. It doesn't really depend on the shape or exactly where you're on the potential. The moment the potential is negative, which is very possible in quantum field theories or very easy to achieve theoretically, in fact, very natural to achieve theoretically. If the moment you have that, you automatically have the condition you want, epsilon greater than 3, and it's not hard to make epsilon large. It could be 10 or 100 or 1,000, which means the contraction becomes extraordinarily slow because the contraction occurs, well, we can choose our time coordinate so that contraction means time is negative but moving towards 0, where 0 would be where we'd have the bounce. As t is getting smaller, the scale factor shrinks as t to the power 1 upon epsilon. And if epsilon is big, that means we're slow. And the bigger it is, the slower it is. Okay, so these are things that the two have in common. They both depend on potentials, although the details of what we need for the potentials are different. They're both essentially equally attainable. Now let's get to the question, the key question. How do we smooth the universe? How does the universe become smooth and flat? Well, let me have you imagine a moment, for those of you that are already familiar with inflation, let me have you imagine that a high school student comes up to you when you're both stepping into an elevator and asks you to explain how it is that inflation solves the smoothness and flatness problems. The student doesn't know any equations, doesn't even know the Friedmann equation I wrote down, but wants an explanation. Try to imagine for a moment what you would tell that student when you only have a brief elevator ride to explain it. I imagine most of you would ask the student to picture the following thing. Imagine space-time is like a sheet, which is curvy and wrinkled and distorted after coming out of the Big Bang. And that what happens is that when inflation aspect begins, what it does is it stretches that sheet so that it becomes smooth and flat over the scale that we observe it. If that's the idea you had in mind, some version of that, sometimes people describe a wrinkly ball or other metaphors, but if this is the kind of idea you have in mind, it's no wonder. It's a very simple idea. It's very intuitive, very easy to learn. It's a very simple idea, very easy to remember. It really, it's hard to get out of your mind as an explanation, and it's easy to teach. So it's no wonder that this idea carries forward. It's one of the things that convinces people that inflation works. The only problem with this idea, despite all its nice properties, is that it happens to be wrong. It doesn't represent general relativity or how inflation works correctly. And it's misleading because it suggests that the only way that you can smooth the universe and flatten the universe is by expansion. And I'm about to show you the opposite is the case. Slow contraction is a powerful method, in fact, a more powerful method of smoothing and flattening the universe. You can tell that something's wrong with this explanation if you think a little bit and realize that I never mentioned in the explanation that the expansion was accelerating. The explanation only depended upon the universe expanding. It didn't depend upon the rate. But in fact, it's very important what the rate is, because when you actually solve the full equations of general relativity, if the universe is decelerating rather than accelerating, the wrinkles grow. They carry their own gravitational fields in general relativity, and the conditions in which the universe is not accelerating but decelerating, that gravitational effect causes the wrinkles and curves and warps to grow rather than to shrink. And in fact, there's been a lot of expansion since the Big Bang. We depend on this effect, in fact, to make the structure in the universe. In the microwave background, we only have tiny little wrinkles in the distribution of matter and energy, but the universe is decelerating in its expansion, and it's that deceleration that causes those wrinkles to grow and become concentrated enough to form all the lumpy structure we observe in the universe today, including planets, stars, galaxies, and clusters of galaxies. So it's not true that simply by stretching the universe or simply by expanding the universe, you can smooth it. But then, as I also say, in order to, the other reason why this idea is misleading is because it also makes it seem like it would not be possible to smooth the universe by contraction. But we'll see, as I said, that the opposite is the case. Now, one of the challenges to understanding exactly how you smooth is that if you begin with a universe which is not smooth and try to solve the equations of general relativity, they'll find that they're too complicated. We can't, with pencil and paper, solve those equations and test whether or not this universe smooths or not. But these days, we do have another set of tools available to us that weren't available to us back in the 1980s when inflation was invented. These are the tools of numerical general relativity, solving the Einstein equations on a computer. When inflation was first invented, already theorists were trying to develop tools of numerical general relativity, but they didn't. There were all kinds of challenges, and it took 35 years before those tools could be developed. And they were first applied to describe the in-spiral and merger of two black holes and the production of gravitational waves, a set of calculations that were crucial for the famous LIGO experiments that first detected gravitational waves coming from the merger of black holes. But in recent years, a group of us, or several groups, including our group, have begun to adapt the tools of numerical relativity to this fundamental problem of cosmology. What does it take to smooth and flatten the universe? There are a lot, recasting the equations of numerical general relativity for this cosmological problem are non-trivial. You can't simply take the code you use for black holes and apply it for cosmology. So it takes quite a lot of development, literally years of development. You have to, among other ingredients, figure out how you're going to formulate the Einstein equations. There are many ways of expressing the Einstein equations mathematically. You have to find one that's optimal for your purpose. In the examples I'm showing, we're going to be using what are called the tetrad formula, the tetrad formulation, for those of you that know what that means. You also have to choose a gauge, a way of slicing time that fits the problem. So in general relativity, you can, in principle, choose your surfaces of constant time or your slicing of constant time as you wish, and it shouldn't make a difference. That's true theoretically, but computers are sensitive to the time slicing, and some, or actually most choices of time slicing will lead to numerical artifacts, things that look like that will crash the program, even though there's nothing wrong physically, simply because you chose an unfortunate choice of time slicing. So you have to figure out an appropriate time slicing that doesn't have that problem. Then after you've done all that, if you've worked out all that mathematics, which already takes a few years, then you have to work on developing a numerical code that's going to be stable and well adapted. And even when you have a numerical code that's well adapted and running, you then have to find ways in which you can measure the outcome. Well, actually, the starting condition and the outcome. You want to make sure you're starting from conditions that are far from smooth and flat and end up with conditions that are sufficiently close to smooth and flat that it's consistent with what we observe. Just to give you a visual sense of what this involves, I've written in compact form the Einstein equations of general relativity in what's called the tetrad formalism. The quantities where you see the capital E's, those are the so-called tetrads that describe space-time. There's a quantity called the lapse. There's a quantity K, which represents the curvature. There's a term sigma. That's going to be an important term that measures the shear or anisotropy caused in space-time in general relativity, and so on and so on. So lots of complicated equations that have to be solved. Horrible, nonlinear, coupled partial differential equations. Then, to add to the challenge, you have to solve in parallel what's an equation for the lapse, which describes the time advance or delay on your surfaces of constant time. And that satisfies a different kind of partial differential equation called an elliptic equation. And one of the hardest things to do in numerical or computational physics is to solve a problem that combines hyperbolic equations like the ones on the left with an elliptic equation like the one on the right. That makes a particularly nasty challenge, which also you have to overcome. And then general relativity has another nasty feature to it, which is you can solve these equations using nonsense initial conditions, conditions that that general relativity doesn't allow because it violates one of the conservation laws. So you also have to check along the way that you're satisfying the conservation laws at each step to make sure that you're solving equations that are actually meaningful. So imagine that this whole process takes, maybe 4 or 5 years to develop. And finally, you get to the point where everything is working and you're ready to show the results of a simulation. So I'm going to now show you some results. So imagine you have a box in which you started off with wild initial conditions. You then either have inflation or you have slow contraction, and you're going to try to follow and see if it manages to smooth the universe. You're solving the full Einstein equations. For your initial conditions, you want to try to choose initial conditions that are far from smooth and flat. Well, in the simulations I'll be showing, I'll be only showing you tracking the conditions in a particular slice through the simulation. It really doesn't make a difference which slice you choose. They're qualitatively the same. And along each slice, I'm going to be representing a slice with 3 surfaces. One which represents the distribution of energy in the field that's driving the inflation or driving the slow contraction. And I'm going to call that combination omega phi. That represents the fractional contribution to the expansion due to the scalar, or expansion or contraction due to the scalar field. Then we have the red curve, which represents the distribution of spatial curvature, and the green one, which represents the shear. A universe which is shearless and curvatureless would be one which only had blue at the top and all the other 2 colors at the bottom. But you see, we're beginning very far from that initial condition. We're beginning with the green, which is the shear, the anisotropy, much higher up, which means there's much more shear than there is anything else in this particular example. It's just one example, but that's the first example we're going to look at. And we're going to now ask, now that we run the equations and we've tried to introduce and we have our smoothing component, what happens to the shear, curvature, and scalar field? So here goes the simulation after the 4 years of effort, 4 to 5 years of effort to get to this point. We hit the start button and we're done. Within instants, we're done. The blue, which was at the near the bottom, is now at the top. The green and red, which represent the curvature and shear, are now at the bottom. This is a universe which now has no curvature and no anisotropy. And it only has a smooth, flat surface, which means it has a homogeneous and isotropic distribution of energy. You saw how fast it went. Let's go. I'm going to show it again. Now you know what to look for. Don't blink. We're done. This is an example of a very powerful smoothing mechanism, which in a matter of instants manages to smooth and flatten the universe. An instance, what would be instants of time in the early universe. What we're looking at in this particular case happens to be not inflation, but the effects of slow contraction. It's a demonstration of the power of slow contraction to smooth the universe. And in this case, I've kind of underestimated the power to make the movie because I chose epsilon to be rather small. The bigger I'd make epsilon, the faster this would go, but then it would be hardly possible for you to see anything at all because within a frame, it would already be smooth. Now, the fact that slow contraction is this powerful in this example is actually puzzling for the following reason. It's an example of what I like to call spooky action at a distance. Many of you may have heard that phrase, spooky action at a distance, when referring to quantum physics. But this is not quantum physics at work. This is general relativity at work, in which quantum physics plays no role. We're solving classical equations of motion. But still, it's a kind of spooky action at a distance because the fact that we're able to smooth the system this way is surprising given what we thought we learned from the case of inflation. Inflation, we learned that in order to smooth the universe, we first of all have to make the universe smooth on scales when the different regions in space, you have to make it smooth over a region which is smaller than a Hubble radius, over the scale of the causal horizon, because we can only make the universe smooth if different points are in causal contact with one another. And then inflation comes along and stretches that reason. But in this case, the universe is contracting. And the horizon is, when we begin, is roughly the size of this ring over here compared to the box, compared to the surface. And the universe is contracting. So the ring is going to be shrinking. The Hubble horizon is going to be shrinking. So you might have expected that you can smooth the universe on the scale of this ring, but you couldn't smooth the entire box because the entire box includes regions which are much farther apart than the diameter of that ring. You should have only been able to sort of smooth maybe a patch of it. And yet what we've seen is the entire box, both within the ring and well beyond, smooth. So what's going on? What's going on is something quite magical that's associated with contracted universes, but not with expanding universes. And it's a quality that we call ultralocality. So if you've learned the word inflation in your study of cosmology up to this point, here is another important word to learn for the future, ultralocality. It's an idea that was first invented in the 1960s and 70s by Belinsky, Kalatnikov, and Lifshitz, who began to study the effects of contraction on general relativity. What they showed is something very surprising, which is that as in a contracting universe, all the terms in the Einstein equations, which involve what we call spatial gradients, terms that tell you something about the difference between 2 points in space, which are the terms which allow different points in space to communicate with one another. connect information with one another, all those terms drop exponentially rapidly as the universe contracts. And if that happens, what that means is that the horrible nonlinear partial differential equations that I showed you now turn into ordinary differential equations. That means they have no spatial derivatives in them. And they're the same equations at every point in space. That's an amazing thing. If you want to make the universe smooth and flat, you suddenly, just by contracting, have every point in space, doesn't care about its neighbors. Every point in space will be solving the exact same equations. This idea was first tested numerically by the work of this group in the early days of the development of numerical relativity. And only recently, in the last few years, has been tested the case for slow contraction. Here's an example of what I mean. Here's just tracking one of the equations in which one of the equations that I had on that transparency, in which there are terms, the last two terms, which have in them, some of you will recognize a symbol that says partial with respect to I. Those are spatial gradient terms. Those are spatial, that's the symbol for spatial gradient. So those are the terms that BKL said were going to fall away. And the other terms are terms which don't have spatial gradients in them. And what the plot shows is that the terms on the right, the two gradient terms, they're falling off exponentially fast as the universe is smoothing compared to the rest of the terms. So the universe is governed by the ultralocal equations, which have no spatial gradients in them and which are the same everywhere in space. This is a proof that ultralocality occurs. Now, slow contraction is also critical because what BKL showed was that if the universe is undergoing fast contraction, they only consider the case of fast contraction. They only consider the case when the universe is dominated by matter or radiation or simply gravity. Those are cases where epsilon is less than 3. What they showed is that when you solve the equations, yes, every point in space obeys the same equations, but they start with different initial conditions. And the outcome you get when you solve the equations is super sensitive to those initial conditions. They are what we call classically chaotic equations, which means although they're obeying the same equations, the universe evolves very differently in different points in space, so-called chaotic behavior or chaotic mixed master behavior. What they missed was the idea if you have slow contraction, the opposite happens. Now, when you solve the equations, it doesn't make a difference what the initial conditions are. Every point in space not only obeys the same equations, but ends up in the same place. And not just any place, in a universe in a region which is flat, homogeneous, and isotropic, exactly the conditions we want. We've seen that when we ran the simulations on the right with slow contraction. Now we're going to take the exact same initial conditions and not just do the case of slow contraction, which smooths, but the case that BKL considered, which doesn't smooth. So here we see just what I was saying, that BKL sort of missed an opportunity of discovering slow contraction and what I think is a fantastic way of smoothing the universe. And just to emphasize the point, we've run hundreds of simulations with different kinds of initial conditions, even ones with incredibly wild conditions, even wilder than you might expect coming out of the Big Bang. And nevertheless, with essentially the same amount of time, slow contraction is able to turn that into a smooth and flat universe. And here's another way of representing it. This is a way in which this is what we call a shear map. Sigma here represents the shear, and a universe which is smooth and flat is going to be a universe which has no shear. So it's going to correspond to the origin in the lower right-hand corner. Each one of these threads here represents tracking a particular point in our simulation, where the red represents where we start, and then the thread shows you how you evolve, how the shear evolves. The quarter circle represents the boundary between regions which are close to smooth and flat, close to the origin, from regions which are significantly far beyond the smooth and flat, as you might expect after a Big Bang. So notice that all the red dots are at or way or beyond, or some of them way beyond what you'd smooth and flat. the kind of wild conditions you'd expect after a Big Bang. But due to the slow contraction, all those threads end up making their way to the origin. Along different paths, but solving the exact same equation, they manage to reach the same final point and find it quickly. Now, what about inflation? Now you should be concerned because what we've seen is that ultralocality plus slow contraction are powerful ways of smoothing the universe. But between the Big Bang and before inflation can start, instead of slow contraction, we have slow expansion. And if slow contraction smooths, causes ultralocality and smooths, slow expansion is going to cause anti-ultralocality and cause unsmoothing. Uh-oh, now we have a problem that we can't just ignore those curvatures in space-time, like you were supposing in the stretched sheet analogy. Those um, those variations can actually fight against the contraction by growing rather than shrinking. So for slow contraction, we saw that even wild variations are able to smooth. But now look at the inflation example. We've begun something much much milder, very gentle variations. And yet, because to get from the Big Bang to inflation, what happens is, just the nightmare scenario we expected. We find things grow, and this interferes with the inflaton managing to take over the universe. As illustrated here, on the left, we see the example of the threads that I showed you before for the slow contraction. On the right, we see the example of the threads, what I've shown you for inflation. Notice the red dots are already inside the circle, so are already pretty close to flat, smooth and flat to start with. We've given inflation a head start. But even then, the threads do not make it to the origin. The universe does not smooth. So, I said at the outset, the 4S challenge for any cosmological theory is to explain the low entropy, homogeneity, isotropy, and spatial flatness of the universe. What we have seen is that inflation fails to meet this challenge, and slow contraction does. In particular, what inflation requires in order to get started is an extraordinarily low entropy, much smaller than the entropy we have today, creating a more serious entropy problem. It requires a universe which is already homogeneous, more homogeneous than what I already showed you in this last simulation. Extremely isotropic, extremely flat, and not just at a particular point, but over a substantial region on scales larger than a causal horizon size before inflation can even start. In other words, the problem of inflation that inflation was intended to solve, the fine-tuned initial conditions required by the original Big Bang model, is what inflation itself requires to begin. This is not progress. We need to have solved the problem before inflation starts. On the other hand, we've seen that for slow contraction plus a bounce, we solve the singularity problem, we solve the entropy problem, we solve the homogeneity, isotropy, and flatness problems through this beautiful idea of ultralocality and slow contraction. And in doing that, we avoid the multiverse and we evade geodesic completeness theorems. We predict no primordial tensor modes consistent with what we observe, and we are compatible with string theory and quantum gravity. So these are the contrast between inflation and the contrast between Big Bang followed by inflation versus slow contraction and bounce is stark. And I think it's a compelling reason why it's time to take the Big Bang out of the Big Bang theory and give serious consideration to replacing the Big Bang with a bounce. Thank you.
Yeah. Thank you, Professor, for your brilliant and truly inspiring lecture. I would like to express my sincere gratitude to you for sharing such profound insights and for enriching us with your perspectives. Thank you once again.
Thank you. Thank you for your attention.
Okay. A gentle reminder to the audience, you may continue submitting your questions by scanning the QR code displayed on the screen. Now we will move to the Q&A session. So, sir, can you please unshare your screen? Yeah, okay. Yeah, the first question is by Mr. Srinjay Paul from the University of Kalyani. He's asking that, is time travel in microscale not possible as to achieve the negative entropy locally? There will be a massive influx of entropy from the global perspective to make the overall entropy increase.
I'm not quite sure what the question is referring to. I think the question might mean, can one have fluctuations in entropy, which are downward fluctuations in entropy? So, for example, could inflation start by some rare fluctuation in some rare region of space, in which the entropy, instead of being what you'd expect after the Big Bang, is the very low entropy you need for inflation to begin? Yes, that's a physical possibility, but it is exponentially unlikely because the difference in entropy is something like 10 to the Google power. So that means the probability is 10 to the 10 to the Google power of producing such a region. And much more likely than that is to produce a region which is smooth and flat without any inflation. So it's actually not, it doesn't help. That possibility is not a good solution to the problem.
Okay. Okay, so we'll take a next question. Okay, this is by Professor Tejendra Singh from the Tata Institute of Fundamental Research. So he's asking that, what decides the energy scale at which the bounds take place? Can this scale be as low as TeV, as low as 1 TeV? Yeah, yes.
Yes, I think it in principle, in terms of just smoothing and flattening the universe, it can be as low as 1 TeV. It can't be much lower because then it would begin to interfere with processes that we have a lot of begin to interfere with um, um, successes of the Big Bang theory, which we don't want to mess up, like the production of the light elements. But TeV is still high enough that it would the theory would still be consistent.
Okay, sir. Thank you. So let's move to the next question.
I should make one other point. Let me just add one other point about that. So
Yes,
in the
yes.
bouncing picture, the universe never reaches infinite temperature. It never even reaches the Planck temperature where quantum gravity becomes important. The universe has a limiting upper bound in its temperature, which is well below the scale at which quantum gravity effects are important.
Okay. Okay. So yeah, next question. So this question is by Mr. Kumar Ravi from Swami Vivekananda University, West Bengal. So suppose one postulates that no physical entity in the universe, including the universe itself, can attain a density greater than that of an atomic nucleus. In that framework, singularities such as those associated with black holes and the Big Bang are excluded. Can this hypothesis be ruled out by current cosmological or astronomical observations, such as the cosmic microwave background or others?
I'd say the problem is we know no reason why there should be this limit, but if there is such a limit, we don't know how to evolve out of it. So if you create once you begin with this high density, you begin with such a large concentration of matter, the gravitational attraction of that matter will resist expansion even more than those wrinkles I was showing you in space-time. So we don't know how to formulate such a theory.
Okay. Yeah, thank you, sir. So we'll move to the next question. Next question is by Mr. Rajat. How replacing Big Bang with a bound solve entropy problem?
Okay, several aspects to this. The first is you never go through the quantum gravity dominated era that caused the entropy problem after a Big Bang. So the big problem you have is that you have a singularity, and just after in the Big Bang theory, and just after the singularity, the universe goes through a phase of quantum gravity domination, which quantum gravity fluctuations produce this very large entropy. And that doesn't occur in the model at all. Furthermore, as you contract the universe becomes more and more homogeneous and smooth. At least the part of the universe on the scales we observe become smooth and uniform and very low entropy. So by the time you bounce, you're at a state of actually very low entropy. Then you convert the energy that's in what was in the slow contraction field into matter and radiation, but that's only a modest amount of entropy consistent with what we observe.
Okay, sir. Thank you.
Good question.
Okay. So we'll move to the next question. Yes. So from the College of Burdwan Raj College. So the question is like, is the entropy of our universe is always increasing at every point of the universe?
No. The total entropy within the universe is increasing. And by the total, I mean both the parts we can see and the parts that we can't see that are beyond beyond what we can observe from where we can observe light or with which we can have causal contact today. The total entropy is increasing. That's the second law of thermodynamics. But you can, especially as structure forms, have regions where the universe becomes more ordered and but somewhere else there must be sufficient disorder so that the average entropy is entropy is increasing, consistent with the second law. So there's no violation of second law happening in the universe on the whole.
Okay, thank you. Thank you so much,
Thanks
sir.
for the question again. Yeah.
Okay, so let's move to the next question by Ms. Pragya from IIT Kanpur. She's asking that, is it possible that a black hole was once a galaxy that expanded and later contracted into a singularity?
This is conceivable, but we don't know of an example that we've observed in the universe that would correspond to this case. But there's nothing that forbids such a thing. Instead, what we see is the early universe has black holes surrounded by matter which form galaxies around them. There's a relationship that most galaxies, for example, our own Milky Way, have large black holes at their centers, but there hasn't been time for it to consume the galaxy, which is what I think the questioner is asking. Thanks.
Okay, let's move to the next question. The question is from Mr. Dept, PRSNC College, Kolkata. So he's asking that matter and antimatter should have been produced equally, yet we observe a strong matter antimatter asymmetry. Why is there more matter than antimatter?
Again, thanks for the question. So this is the assumption that matter and matter should have been produced equally is the weak point of this argument. That depends on there having been a symmetry in the laws of physics between matter production and destruction and antimatter destruction and production. And that was an idea we had back, let's say, in the early 60s. But already by the early 70s, we realized that matter and that there does not have to be such a matter and antimatter symmetry in fundamental physics. In fact, we have very strong reasons to believe there is no such thing. And because of that, because it's possible to have what we call baryon number violation or an asymmetry between matter and antimatter, you can generate that asymmetry that we observe dynamically. There's, in fact, not a unique explanation. There are a handful of different examples which use that idea to generate the observed matter and antimatter asymmetry we observe, and that can be fit within either the Big Bang inflationary paradigm or the slow contraction bouncing paradigm.
Okay, thank you, sir. Let's take a last question. The question is from Ms. Shweta from Star Spaces Experience, and She's asking, "Hi sir, you spoke about ultralocality. My humble and simple question is an ultralocal state, different regions of space effectively stop communicating with one another. Paradoxically, you argue this leads to a more uniform universe. Could you explain the intuition behind how less communication between spatial points results in more homogeneity across the entire cosmos by the time of the bounce?"
It's a very perceptive question because you might worry, in fact, that we were taught, we were taught when we were studying inflation, we were taught just what you suggest, that if you were to take points which are not in communication, there's no way to smooth them. But what's missing is the idea of slow contraction. So it's not just that the equations become ultralocal. It's that in the background of slow contraction, those equations have what we call an attractor solution, a single outcome, which is special, which every point is drawn to independent of the others. And it happens to be, in the case of slow contraction, one which every point in space in its most immediate surrounding is going to be flat and homogeneous and isotropic, so that when you look at the collection of points, they all end up at the same place. They get there at different times, as I showed you with those threads. They weren't all tracking in parallel to one another. They get there at different times, but they all get there in an overall short period of time. So it's the combination not just of ultralocality, but add to that slow contraction. It would not be the case, for example, if it were fast contraction, like I showed. But thanks for the great questions.
Thank you, Professor, for addressing these questions with such depth and clarity. We still have more questions from the audience, but due to limited time, we will conclude. So on behalf of the Bhaktivedanta Institute, I would like to once again express our sincere gratitude to you for sharing your insights and wisdom with us today. Your lecture has given us deep insights into science and our understanding of the universe, and we are truly grateful for your time and generosity. Thank you very much, Professor Paul.
Thank you, and thank you for your attention and the opportunity.
Thank you. Thank you.
Bye-bye.
Now, moving forward with today's program, we have another fascinating talk lined up. Our next speaker is Professor Pankaj S. Joshi. He will be speaking on the topic, the story of black hole, life and death of massive stars in the universe. Next slide, please. So before we proceed, I would like to request all the participants to please scan the QR code displayed on the screen to submit your questions to the speaker anytime during or after the lecture. You may take a screenshot or a photo of the QR code. Alternatively, the Google Form link has been shared in the chat box. Before inviting him for this lecture, let me briefly introduce Professor Joshi. Professor Pankaj S. Joshi is an eminent Indian physicist and cosmologist and a leading authority in general relativity, gravitation, and cosmology. He is currently Distinguished Professor of Physics and Founding Director of the International Center for Space and Cosmology at Ahmedabad University in Gujarat, where he leads research, training, and public engagement in fundamental questions about the universe. Before joining Ahmedabad University, Professor Joshi was a senior professor in the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research, TIFR, Mumbai, where he carved an international reputation for his work on the gravitational collapse of massive stars and the nature of space-time singularities, including insights into black holes and the possibility of naked singularities. His research has been published in more than 200 peer-reviewed papers and major monographs from Oxford and Cambridge University Press. Invited by Stephen Hawking to work at Cambridge University under a Nuffield Foundation Fellowship early in his career, Professor Joshi has also held visiting positions at top institutions across the UK, USA, Japan, Spain, South Africa, and Italy. He is a fellow of leading scientific academics and a recipient of prestigious awards, including the INSA Vainabappu Memorial Award. Professor Joshi's contributions span deep theoretical advances and wider science outreach, making him one of India's most respected figures in theoretical physics and cosmology. Without any further delay, it's my pleasure to invite Professor Joshi to deliver his talk.
Thank you. Can you hear me?
Yes, Professor.
Okay. I would like to warmly thank the Bhaktivedanta institution and all of you for this wonderful opportunity to be able to talk to you. I'll share my screen. Can you see my screen?
Yes, sir. Can you please make it full screen?
Okay. In order to do that, I think I
click on this play.
I go on the view. Is that all right?
Maybe can you try clicking play on your this?
Yes.
Yes, that's perfect.
Okay. So we will talk about the stars and the universe. There is a curiosity, as we know, right from the beginning on the stars, what they are. In the earlier days, we had the celestial sphere, and looking beyond the celestial sphere was kind of forbidden, unknown forces might be there. But then it's in the nature of men to ask questions, to find out the laws of universe, and the quest continues. As of today, we have wonderful missions on the earth as well as out there in the cosmos, where we probe the universe to very depth, millions of kilometers away. We try and see. This is, of course, the Hubble Space Telescope, and this is the Chandra telescope, which observes the skies in X-rays. But apart from this classic instruments, many new projects are coming up, and some of them are already operational. They are square kilometer array, TMT 30-meter telescope, LIGO. LISA is in the, workings. Even more importantly, the Event Horizon Telescope to observe the centers of the galaxies. I will talk about that. And also such others. The most important difference that has taken place because of all these missions is that we have started now on the, on the deepest places in the universe, but at the same time, very strong gravity, ultra strong gravity regions of the cosmos also we are really looking at. When we look deep into the skies, beyond what you see actually with naked eye, you see the dots in the sky, the telescopes show not only the stars, but also what are called nebulae. And many of these objects that you see in this picture are actually big, massive galaxies. This is a close-up of the previous picture. And each one of these galaxies, in fact, are 400 to 500 billions of stars. This is one of such galaxies. This is another Galaxies come in various shapes and sizes. It's a huge issue today. So much data is actually coming in, but AI might help us to, process this data much more effectively. There is a competition between the technology and the data coming in, so to say. But today I will focus mainly on stars rather than galaxies. And why stars? We will talk in a moment. The stars really and the black holes we will be talking about, which are at the centers, which could be at the centers of the galaxies. These are the objects which are of greatest interest today. The point that I wanted to make was that stars are sun-like, but then much bigger star than the sun, like the Sirius, Pollux, Arcturus, and so on. They all exist in the universe. Now, the life of sun is about 5 billion years today, and it is still going to live another 5 billion years. However, if the star is much more massive, say 10, 20, 30 times the mass of the sun, then its life is much shorter. In fact, it will live only, say, 10, 20, 30 crores of years, depending on its mass. The more the mass of the star, the faster, quicker are the internal burning processes within the star. And then what happens is that when the, nuclear fuel within the star exists, then the star starts contracting under its own gravity. This is just another picture showing the size of Earth in comparison to Sun. So, how small the Earth is, and still so many things happening today on the Earth. As we all know, today, the point is if we realize how tiny we are on the scale of cosmos, probably, our egos can become smaller. You have just heard probably, the Big Bang theory and the origin of the universe. The universe is supposed to have originated from a Big Bang. Eventually, galaxies formed. And of course, we have Large Hadron Collider like experiments which also probe the very highest collisions of elementary or basic particles, so to say, in the universe. The key question, which has been one of the most prominent issues in cosmology as well as astrophysics, is what happens when a massive star dies. As I told you before a moment, very massive stars, like 20 or 30 times the mass of the sun, their lives are pretty short. It's like a balloon. You see, when you release the mouth of the balloon, the air goes away and the rubber contracts the size of the balloon. Similarly, a star that was existing for, millions of years, within seconds or minutes, it contracts or collapses catastrophically under the force of its own gravity when its internal nuclear fuel is gone. What happens when such a star dies? In fact, Subramaniam Chandrasekhar's work, early work in the 1930s, was related to, the final fate of sun-like stars. He pointed out that such stars collapse into a stable configuration. The stars which are about 1.4 solar masses, they result into white dwarf size, which is about 1,000 kilometers. Our sun also will one day become a white dwarf. its outer layers will be thrown away, engulfing the planets around. In fact, Chandrasekhar pointed out, you see, that it must be taken as well established that the life history of a star of small mass must be essentially different from the life history of a star of large mass. So this was pointed out way back in 1935, that large stars, their life histories, you see, remains a big question. As he says at the end of this para, a star of large mass cannot pass into the white dwarf stage, and one is left speculating on other possibilities. So this has remained one of the most important questions in astrophysics and cosmology, also related to you see, the high energy astrophysics. This is where what you have to do is to study the gravitational collapse of a massive star. And what is the final fate of such a star? This question was studied using general theory of relativity, because the gravitational fields are so strong that you need Einstein's theory of relativity. And in fact, this entire question is absolutely fundamental to the modern theory and the astrophysical questions related with black holes. Einstein theory has to be used. The key point is it is dealing with the curvatures of space and time. I cannot go into the details of the same, except I'll show you a few equations of the theory. But we are familiar with positive, negative, as well as you see, flat surfaces. This is a kind of generalization, Riemannian geometry, dealing with the space-time continuum, the four-dimensional space-time manifold. And of course, Einstein gravity has important manifestations such as black holes, Big Bang, gravitational waves, and the shadows at the center of the galaxy. In 1939, Oppenheimer and Schneider wrote a paper showing that there is a continual collapse happening. Then in that case, you see, the entire spherical mass, the star, if you call it that way, will collapse to what is called a space-time singularity. When this singularity forms, before the singularity has developed, what will happen is an event horizon will happen. An event horizon will form, so singularity will be necessarily covered. What is singularity? It's a event, it's a place, it's a happening where all the mass of the star, according to the general theory of relativity, will be concentrated, you see, collapsed. It was the so-called cosmic censorship due to Roger Penrose and also Stephen Hawking, at least partly, that they conjectured that when you consider more realistic collapse, I say more realistic collapse because the Oppenheimer and Schneider's work was based on very many special assumptions. That is, the star is completely spherical, the star is completely homogeneous, it is made of matter which is only dust, that is, it has no pressure, so on and so forth. And then what happened was the star collapsed and the singularity formed. However, before the singularity formed, what is called an event horizon developed, and what you have is what is known today as a black hole. This outer surface that you see is the event horizon, from where there is no light supposedly escaping. When you say that we see the black hole, it is really the light which is coming from the accretion disk that is circling the black hole, but from within the black hole, where the singularity is also hidden, nothing can be seen, nothing can come out. This hypothesis was taken extremely seriously, namely that always the black holes will develop whenever the massive stars die, and this became actually the basis of physics and astrophysics of black holes. Well, John Wheeler, Roger Penrose, Stephen Hawking, Kip Thorne, and many others contributed to the classical and quantum aspects investigations of black holes. Even thermodynamic analogies happened. So there will be a singularity at the center of the black hole. There is what is called an event horizon that you see, and out there is what is called the photon sphere. So the standard paradigm is average stars will, the upper, you see, panel, they will become red giant, planetary nebula, and white dwarf, whereas massive stars would become red giant, supernova, and black hole. And I have, you see, not talked about it, but they could also, I mean, if the star is about 8 to 10 solar masses, it could become what is called a neutron star, on which further matter could accrete, and then it could again become a black hole. But mind you, this is still a hypothesis. In general relativity, there was a proof by Roger Penrose that whenever a star collapses, by, I mean, what are called singularity theorems, by Roger Penrose, by Stephen Hawking, and Robert Garrosh in USA, the theorems say that when massive stars collapse, what should develop is a space-time singularity. And also in early universe, such singularities will form. But mind you, nobody proved really that when massive stars develop, a black hole will develop. That is, an event horizon covering the singularity will happen. So the cosmic censorship remained a hypothesis for decades, I think by now almost 5 decades, and it remains one of the most unresolved issues in modern astrophysics and general theory of relativity. There is no proof, so to say, for this hypothesis. All the same, the scientists were fully aware that this issue remains open, namely, do all massive stars collapse to black holes? So, you have to, when you ask this question, you have to take inhomogeneities, the internal pressures, and you see other factors, physics of star. And in past decades, much work has happened, including our own work, the work of myself and our collaborators and students and so on, as well as many international groups. And what turns out is that typically when you consider more realistic collapse as compared to the models considered by Oppenheimer and Schneider, then in that case, in some cases, the singularities that form are covered by the event horizons, but in other cases, it is not covered by the event horizon. It all depends on the internal dynamics and the internal constitution of the star. To give you an example, if the star is completely homogeneous in its density, say right from center to the boundary, if you take the Oppenheimer-Schneider model, it was that. Then it will become black hole. However, if you have the same dust configuration, pressureless dust configuration, with density somewhat higher at the center and then decreasing away from the center, which is the realistic, astrophysically realistic configuration, then a large number of models have been worked out where, in fact, the event horizon is delayed and the singularity becomes visible part of the time. Then it can be covered, or in some models, in fact, it could be visible for a long time. Now, all these issues have fascinating consequences in the sense that if it is black hole, how it will affect the dynamics of galaxies and their centers. If it is a singularity without a horizon, which are nowadays called also horizonless compact objects, or you see, purely singularities, rather than calling them naked singularities, they would have immense astrophysical applications. I cannot go into the details of this due to the limitation in time, but partly we'll try to cover it in the question answer session, or maybe even later. But here the first equation, you see, includes the inhomogeneity in the density configuration, and the last equation here tells you that in that case how the you see event horizon is affected. Let me skip this slides, but just tell you that so many models by now have been studied both analytically as well as numerically with different equations of state. You see spherical stars as well as non-spherical collapse models. They all have been studied. The key point is, what turns out is that depending on what the initial data is, what the, you see, initial configuration is, depending on that, either a black hole or a singularity will develop. So you see, here is the initial surface, that is the time from where the star starts collapsing. So depending on the velocities of the shells and depending on the densities and the pressures, you see, either the event horizon will form or will not form. In the, you see, space of initial data. By space of initial data, I don't want to become too technical. It is just what the densities are and what the pressures are from which the star starts developing. So, you see, these are the singularities without horizon, and you see the upper part is black hole. So you can see that, each of them develop. We have had, you see, many discussions with eminent, you see, physicists. In fact, in a recent interview, Roger Penrose, in fact, pointed out, this was the interview to New Scientist. I will not show the that part of interview here because it will take, you see, a few minutes. But he actually pointed out that, you see, he was well aware of this question, and in fact, he only asked a question whether a massive star will become a black hole or it will become a singularity without a horizon. I would urge you to seek out. I can, send the link to the organizers who can, post it to the participants. But he clearly, accepted the, Professor Penrose accepted the possibility that both black holes and singularities without horizons can occur. So to modify the previous picture, heavyweight stars will go either to black hole or exploding fireball. Now, why I call it exploding fireball? If the singularity is visible, so much density, so much, you see, temperature, so much happening will be there that quantum gravity effects could make it explode, as I'll point out to you. It's a very emotional subject, a very hotly debated subject. When Stephen Hawking accepted that, yes, such singularities can develop without horizons, it became first page story for New York Times. I ended up, because of our, work in this area for quite a while, writing, you see, monographs for the Cambridge University Press as well as the Oxford University Press. Based on that, I ended up again writing an article. I was invited by the Scientific American, 170 years old, venerated magazine of US, and interestingly, they made it into their international cover story. This is the German cartoon as well as the title page. And interestingly, in US, a lawyer, Sergio de la Pava, wrote a novel which attracted quite some attention, and recently even a movie has been made. So this was all theoretical background. By now, it is well accepted. I think it would not be exaggerating to say that people are exploring both black holes as well as horizonless compact objects. The key point, many of you will ask, all right, these things can happen. So what? What we are going to observe out there in the skies? Are there going to be observational signatures? If the singularities are there without horizons and so on. So what are the observational and astrophysical implications? Can we distinguish them, in fact, in the skies? So as I said, the answer is possibly an affirmative, at least in the sense that a large number of efforts have taken place to decipher and distinguish the accretion disk properties around black holes and singularities, high energy particle collisions around singularities have been examined. Gravitational lensing around this object has been explored. Most importantly, shadows. You see, the latest excitement is the Event Horizon Telescope probing the center of galaxies. Our work with Professor Ramesh Narayan of Harvard and Daniel Malafarina has shown that singularities also can cast shadows which are similar to black holes. And in their latest series of papers showing the pictures or photos of images of, our galactic center black hole. The Event Horizon Telescope series have cited our papers. The accretion disk differences are very striking. If you had a Schwarzschild black hole, as you see in the inner part dotted lines, a Schwarzschild black hole, energy will stop coming because of what is called, the photon sphere and inside ISCO, innermost stable circular orbit of the matter accreting around the object, the black hole. However, in the case of a singularity that is visible, the stable circular orbits extend way below, very close to the singularity. As a result, you have much more powerful emissions in very high frequency energetic outcomes. You can see this in, some of our papers. High energy collisions have been examined, and it is seen that, without fine tunings, you can have a very, very high energy collisions in the vicinity of a singularity. This is as opposed to the black hole case, where you have to do a lot of fine tuning actually if you were to observe the high energy collisions. Gravitational lensing has been studied in great detail earlier around black holes, but now also around the singularities. Why all this is so important? So that is the point I come back to probably again. this so-called cosmic censorship is absolutely fundamental to the modern theory of black holes, is its astrophysical applications. So, I mean, after all this gravitational collapse model, the study of all this gravitational collapse models, if at all in some form the cosmic censorship is correct, it will, you will have to avoid these models. So you will have a very fine-tuned version of censorship. But on the other hand, you see singularities without horizons are available, visible. If they arise in nature, then there could be exciting observational implications, which are in fact already being studied. Key point, general relativity implies existence of space-time singularities, strong gravity regions, where both quantum gravity and general relativity in fact come into their own. At this low energy scales on Earth and planetary system and so on, you don't observe this quantum gravity effects. But near singularities, this will be really, really important. Now, if this are visible to external observers in the universe, then it could have very interesting consequences. As Robert Wald pointed out, if censorship fails, then in a literal sense we would come face to face with the laws of quantum gravity, where whenever a gravitational collapse to a naked singularity occurs in distant regions of our universe, we have called these objects really quantum stars. That is, when singularity becomes visible. Star collapses, exciting observational implications, and high energy explosive cosmic phenomena should be observable. Does nature produce a quantum star whenever a massive star collapses? We studied quantum gravity effects near such a horizonless singularity, and what we actually showed was effective pressures are so huge negative that a burst-like scenario actually develops. So there is a tentative comparison, tantalizing comparison with so-called gamma ray bursts. Many such possibilities are under exploration at the moment, which you can see on the Google or on the archives. Is this a quantum gravity lab? Worth asking a question. We have not been able to make good progress with string theory or loop quantum gravity, on purely theoretical basis. But if you observe, if the nature has provided us with a quantum gravity lab, and if we do observe some, signals coming from ultra dense gravity regions, in that case, possibly we can, derive a better theory of quantum gravity with more realistic observational input. I will come to, the latest part, which is in fact the Event Horizon Telescope observations of the center of our galaxy. This is a collaboration which puts together radio telescopes across the globe and tries to explore and see and examine the very center of our own galaxy as well as M87. These are the two galaxies which have been probed. They have images something like this, as you are aware. I have discussed many of these aspects in, one of my books, which is a popular, semi-popular book published by Oxford. But the point is that what we have shown is that not just the black hole, but the horizonless compact objects, that is the singularities or compact stars, also produce such images, in fact. And this has been a matter of a great discussion. In fact, in their papers, the Event Horizon Telescope did cite our papers saying that the one of the singularity models that we proposed, that is by Joshi, Narayan, Ramesh Narayan, and Malafarina, that has been one of the best mimickers of, you see, the galactic center object. Trajectories of stars have been studied. You see, we are talking about some of the observational implications of the singularities as well as black holes. They have been studied, and is a very interesting phenomenon pointed out by one of our, you see, collaborators, Parth Babania, that there could be negative precision when you are dealing with a horizonless compact object. And this is again an intriguing happening. Coming to gravitational waves, you have many of you have seen this, you see, observatory LIGO picture, the massive objects coming together and colliding and producing data, which is, you see, the signatures of the gravitational waves being produced. Kip Thorne, in fact, has been very, very open to the idea of, you see, both black holes and singularities. In fact, in one of his talks, he pointed out that if you consider the trajectories around a black hole, they will have, the waveforms will have a certain variety or certain profile. However, and this is, by the way, a slide from Kip Thorne's lecture. He asked this question, that what if the central body is not a black hole? For example, if it is naked singularity. So in that case, he conjectured, and several investigations are going on as to, you see, how and what kind of, you see, trajectories will happen around such singularities without horizon. So he pointed out there could be a very wildly different map emerging. Now, you see, probing the galactic center is one thing, as I showed you here. You see, this is one thing, because the smaller the object you want to examine, you see, the bigger must be the size of your telescope. If you want to explore the center of our own galaxy, then what happens is you must have a telescope which is so large as the size of the Earth itself. And only then you can create an image which is something like what the Event Horizon Telescope reported. However, if you want to explore actually an object like this, when I say object like this, what do I mean? When a star collapses and produces a black hole. You see, these are called stellar black holes. This object is a star-sized black holes which would have mass of, say, 5, 10, 20 solar masses. However, the black hole here, you see, will have millions of solar masses in the in its total mass. So this is a galactic black hole. It is also called a supermassive black hole. So supermassive black holes could be there at the centers of the galaxies. But then when you want to observe a star-sized black hole, you see something like this, then it is impossible to figure this out. It is impossible to figure this out using, the telescopes that we have on Earth. You can't actually get the image of such an object, because the resolution required would be extraordinarily, finer as compared to the galactic size black hole. But you will know the properties of such objects only through what are called accretion disks. That is, the disk that is, the matter that is, rotating around the black hole, is something like this. Here is a singularity, and there is all the matter circling the singularity, and somewhere out there could be an event horizon, or maybe it is not there. Who knows? It depends on the configuration of the gravitational collapse that created this singularity. So the property of the accretion disk will allow you to decipher the nature of the object, and that is where you see a lot of work is being done. By the way, for this book, I also requested Oxford to produce an Indian edition. This has been reviewed by Nature, by Physics Today, and so on. I hope the Indian edition may be still there. But the important point that I am trying to make is that now various groups, throughout the globe, for example, polarized image of equatorial emission in horizonless spacetimes. So what are the signatures? What are the kind of polarizations? How the images are working and operating? So many such questions are being probed by many different groups using both analytical as well as numerical methods. We have many of our collaborators, students, postdoctoral fellows, who very excitingly and interesting contributions they make. I think for the moment I should stop here, and maybe if there are any further interesting points as we go ahead, then we will discuss these issues. Thank you very much for again this wonderful opportunity.
Thank you. Thank you, Professor, for your brilliant and truly inspiring lecture. And I would like to express my sincere gratitude to you for sharing such profound insights and for enriching us with your perspectives. Thank you once again.
Thank you.
So now, a gentle reminder to the audience. You may continue submitting your questions by scanning the QR code displayed on the screen. Alternatively, the Google Form link has been shared in the chat box. Let us move to the Q&A session. Yes.
Okay.
Yeah, this question is by Mr. Louis Marmot from the York University. He's asking, thank you for this very honest presentation on the assumptions involved in the hypothesis of black hole formation. We do observe dense mass concentration in astrophysics, AGN, neutron stars, etc. But is it possible that a black hole never has time to form?
Yes, yes, that is definitely a possibility that the you see black hole may not have time to form, or the star may evaporate entirely. You see, before the collapse actually happens. Uh, But by and large, it has been accepted that when such a massive star is there, out there, and it has existed its nuclear fuel, then in that case, such a catastrophic collapse occurs, and there won't be enough time for all the matter to be radiated away. Uh, Therefore, in fact, the black hole paradigm is gained so much of power. Uh, the event horizon must form, the singularity must form. This is the crux of singularity theorems of the Penrose, Hawking, Garrosh. That you see, if the trapped surfaces form, then the singularities must develop, unless there is a very violent uh, disruption of energy conditions. If the quantum gravity gives rise to very strong negative energies, then only the singularity can be, or the black hole can be halted. And that is why you see the so many astrophysical applications of black holes came into being. Catastrophic gravitational collapse is the key thing.
Okay. Okay. Thank you, sir. So let's move to the next question by Dr. Bharat Pandey from Government PG College, Raniket, Uttarakhand. So he's asking, if black holes are the final stage in the life cycle of massive stars, do they truly represent an end, or could they actually be a transition phase where matter and information are transformed into something where we do not yet understand? In that context, how does this idea connect with current theories about information laws and the possible existence of new physics beyond our observable universe?
Definitely, the physics very close to the singularity, which might be hidden within the black hole, is unknown as of now. Uh, Whether a black hole would transit into something even more mysterious is an open question. Uh, there have been issues, and there have been conjectures even regarding the you see transition to another phase. Uh, but theory which really works out the you see the consequences, it is yet to be formed. There are issues, I mean there are questions, wormholes, and you see the loops, the topological tubes, and many other possibilities have been discussed. But yes, it's still an open question.
Okay, thank you. Thank you, sir. So now let's move to the next question. Question, please. Yeah, this is Mr. Ajay from Department of Physics, SVNIT Surat. So he's asking, why is that when something entering a black hole stretches in its front and back like a rubber band, if it is due to its strong gravitational pull, why is it not in the case of massive stars?
Yes, near the black holes, you see the gravity grows enormously. So typically, you see this so-called gravitational tidal effect is always there. That is, if you have a rod hanging in a gravitational field, and the one end pointing to the center of the object, then the gravity at the closer end would be higher than you see the gravity at the other end. But this is a very minute difference in gravity. When you are really near a black hole, then this difference, or the gravitational tidal difference, grows so enormously that it really stretches away the object. So it is the difference really in the gravitational pull at the both ends of the object. And this is why you may have seen the pictures that the man falling in the black hole is completely stretched, you see, and becoming like a line.
Okay, thank you. Thank you, Professor. So now let's move to the next question. This is by Miss Sweta from Starscribe Experience. Thanks for such an amazing lecture. My question is, you have long argued that under certain conditions of stellar collapse, a naked singularity can form instead of black hole. If the Event Horizon Telescope (EHT) continues to provide images that look like shadows, how can we observationally distinguish between the shadow of the traditional Schwarzschild black hole and the naked singularity that might be mimicking that same visual signature?
Yes, this is in fact a very interesting frontier. How do we distinguish shadow that has been created by a singularity as opposed to that created by a black hole, even though they may look similar in sizes, in the in their appearance and so on. What some groups have been probing, as I am mentioning, as I mentioned during the talk, right now many groups you see around the globe have been exploring these possibilities of distinguishing these two objects from each other. Now, the point is that these gravitational fields are described by, you see, what are called the geometry of space-time. Like the Schwarzschild black hole is described by what is called Schwarzschild geometry. There is a particular metric. It is called, gravitational potentials are there in the geometry, which describe what kind of gravity is there as you move from point to point. So the gravitational potentials of the Schwarzschild geometry are quite different from the gravitational potentials of a singularity spacetime, that is a horizon-less compact object. And you see, one difference that I pointed out to you earlier in the talk, if you remember, is that the accretion disk extends way below, inside, very close to the singularity. The stable circular orbits extend way inside. So that is why the output of the accretion disk is quite different in the black hole case and the singularity case. However, further, when we have, for example, you see, the other finer images, you see, of the central object, which is at the center of the galaxy, then if it is, you see, a singularity, naked singularity or a horizonless compact object, then there will be some very definite differences arising as compared to the Schwarzschild geometry. In fact, some groups are already exploring these differences. And this work or this, earlier, you see, I should tell you a little bit of, history, in the sense that even though I might have, you see, pointed out to you some results, it has been, a very standard assumption in the field that, well, if the massive star has collapsed, then it must be a black hole. But of course, everyone agrees that it's a conjecture and it's a, hypothesis. Now, all that we have done is we have explored, and also many other groups. So it's not just me that I have argued, it is the group of scientists at various places by now. Numerical You see efforts even from Oxford, Cambridge, even at Princeton. You see Institute of Advanced Studies, detailed numerical simulations have been carried out of collapsing objects. In fact, in string theory today, it is widely accepted, the results have been there, that in the dimensions higher than 4, naked singularities are extremely common. In string theories, that is the result today. So by now, the subject is much bigger, in fact. So I am just an insignificant, part rather than my arguing. So it is the, it is true though that I have worked on these issues for many years. So the key point that I was trying to make was the finer differences in the images of a black hole and horizonless compact object. This will come out when we do further analysis. And because Event Horizon Telescope has cited our papers now as the best mimicker, so the attention has been drawn. And now these investigations have begun. Yes, but it's a frontier question. Thank you.
Thank you. Thank you so much, sir. So now let's take one last question. This is by Mr. Kumar Ravi, and he's asking that suppose we postulate that no physical system in the universe, including the universe itself, can reach a density greater than that of an atomic nucleus, thereby eliminating singularities in black holes and the Big Bang. Would such a hypothesis still be compatible with the key black hole observables such as gravitational waves detected by LIGO, shadow imaging by the Event Horizon Telescope, and the orbital motion of stars around Sagittarius A, or can it already be ruled out?
Interesting, a very interesting question. In fact, the possibility number 3 that you have mentioned, the orbital motion of stars around Sagittarius star, it kind of fairly definitively point to the existence of extremely high dense plasma or the matter close to the galactic center. And again, you see, if you see this particular book, you see that I showed this Oxford University Press, or the book by Kip Thorne on black hole, time warp, and you see other issues. If you see this, Kip Thorne argues very, very strongly as to why a catastrophic gravitational collapse must give rise to ultra-dense regions in the universe. However, people have tried throughout to avoid and resolve space-time singularities. My final say, well, not final say, but it is subject to the, I would say the strongest possibility would be that when the densities grow sufficiently high in the gravitational collapse, then the quantum gravity effects will take over to really resolve the space-time singularities. But still, this will be extraordinarily high densities, way, way beyond the, you see, the usual atomic scale densities. Thank you.
Thank you. Thank you, Professor, for addressing these questions with such depth and clarity. We still have few more questions from the audience, but due to limited time, we will conclude here. On behalf of Bhaktivedanta Institute and all the participants, I would like to once again express our sincere gratitude to you for sharing your insights and wisdom with us today. Your lecture has given us deep insights into our science and understanding of the universe, and we are truly grateful to your time and generosity. Thank you very much, Professor Joshi.
Thank you. Thank you so much. I thank all of you and the Institute. Thank you.
Thank you. Thank you, sir. So now, moving forward with today's program, we have another fascinating talk lined up. Our next speaker is Professor Andrei Linde from Stanford University, USA. He will be speaking on the intro topic Universe or Multiverse. So, Professor, can I please introduce to you to the audience
Yes.
in a okay. So,
Oh,
can you please unshare the? Can you please unshare the screen, sir, if you don't mind?
okay. So my name is Andrei Linde. I am a professor of physics at
I'm
Stanford
sorry.
University.
I'm sorry. Actually, can I introduce you if you don't mind?
Oh, yeah, sure.
Okay. Thank you so much. So, so next slide. So, Professor Andrei Linde is the Emeritus Professor of Physics at Stanford University and one of the seminal architects of the modern cosmology. He is the originator of the chaotic inflation theory, a paradigm shifting framework that revolutionized our understanding of the Big Bang. Linde demonstrated that the exponential expansion of the early universe does not require fine-tuned initial conditions, but arises naturally from the dynamics of scalar fields. His work corrected the fatal flaws of the earlier models, firmly establishing inflation as the standard explanation for the uniformity and geometry of the observable cosmos. Linde's theoretical vision extends beyond a single universe to the concept of the eternal inflation, which posits that the cosmos is self-reproducing fractal multiverse. He showed that quantum fluctuations in the inflationary field continuously spawn new exponentially large parts of the universe, potentially with different physical laws. A recipient of the Fundamental Physics Prize, the Gruber Prize, the Kirby Prize, and the Dirac Medal, Linde's contribution have fundamentally altered humanity's conception of our world, providing a mechanism that explains the origin of the large scale structure of the universe. So, with this, I would request Professor Andrew Linde to start his lecture.
Hello. Thank you very much for introduction, and thank you very much for inviting me to give this talk. So I will start my talk with showing you the picture, which is right now became pretty standard in explaining the different stages of the evolution of the universe, starting from the Big Bang. So here is a Big Bang, and maybe simultaneously with the Big Bang, this was already a stage of inflation, which is exponentially rapid expansion of the universe at the very early stages of its evolution. Now, to understand why it is so, and also to explain the title of this talk about the universe and multiverse, I will first start with the citation of some quote from Albert Einstein, which was written not long before he passed away. He had written autobiographical notes in which he said that, and I will read here, I would like to state a theorem which at present cannot be based upon anything more than faith. That's amazing when somebody of Einstein's stature say that cannot be based on anything more than faith in the simplicity, in intelligibility of nature. There are no arbitrary constants, etc. So what I will stop reading it. The main idea is that the universe is given to us in one copy, and we're trying to find out the reason for that, and we're trying to find out why the mass of the electron at far left from us a galaxy and a distant galaxies to the right of us, everywhere in the universe, mass of the electron is the same, charge, electric charge of the electron is the same, other coupling constants, other constants of nature, masses, everything is, well, do not change. It's everywhere the same. So maybe there is some real principle which explains why it must be so. And one of the main goals of inflationary cosmology, which I would like to discuss today, was to explain why indeed the universe is everywhere the same, and thus to realize at least some parts of the Einstein's dream, to explain why indeed in different parts of the universe you have the same laws of physics operating. And we have developed this theory, and after that we were up to a surprise that some constants of physics may be fundamental, and some constants of physics describe just what happens at our part of the universe and may be different in different parts of the universe. So I will start with why do we need inflation? And I can tell you the basic of the theory which we have developed during last 45 years. So this is the standard picture which is often used to explain how do we perceive expansion of the universe. The universe expands in all different directions from every single, and that is strange, from any single point in space. When you look, you live in one part of the universe or another part of the universe, you will see galaxies are always moving away from you, as if the whole space is expanding and they are moving away from any part of the universe. And then if we try to describe this numerically, and maybe what do the following. When the universe expands, what's if we run movie back in time? Here the universe originally was smaller, smaller, smaller. So when we run movie back in time, we see the time where the galaxies were very close to each other. Actually, they were smashed each other. There were only elementary particles flying. The universe was very dense, and there was some moment which is called Planckian density. That we cannot even go beyond this Planckian density using present state of physics. At this Planckian density, which happens also at the time 10 to the minus 43 seconds from, and that is from if there was a Big Bang. So we come very close to something, and then movie stopped working. We do not know what was there. So this was a Big Bang. And now if we, using this standard theory of the Big Bang, calculate which part of the universe I was able to see, or whatever, imagine somebody looking at that time at the universe, we will see that this person will be able to see only at a distance 10 to the minus 33 centimeters, because the universe is so young and the light traveled only at this distance. And the size of our part of the universe, if we play it back, at that time was not so small. It was about 1 centimeter or so. So then one can see only tiny, 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 tiny fraction of the universe at this Planckian moment. And this tiny part will contain only 1 elementary particles, or maybe 10 elementary particles. But at the moment we have 10 to the approximately 10 to the 90 degree of elementary particles. So if I would like to do something with the universe, making it homogeneous, large, whatever, I would be unable to do it because I, or whoever tries to do it, can affect by anything that he does only 10 to the minus 90 of all particles in the universe. So that's the problem with the standard Big Bang. It's very, very difficult to imagine why this universe emerged that way, why it was so large, why it contained from the very beginning so many particles, why different properties of the universe in different parts of it were the same. And that is why I will skip it. And that is why inflationary universe theory came as a possible solution of it. So the standard Big Bang cosmology can be illustrated by this picture. Suppose you have a box with, for example, 1,000 protons. Universe expands and the box grows in size, but it still contains 1,000 protons. Nothing more, nothing else. The total number of particles in the standard Big Bang cosmology practically did not change. Maybe changed it twice or three times during the whole evolution of the universe, but you get right now the same particles that were before. And that is why it was very difficult to explain the origin of the universe. And there are many different problems about this Big Bang theory. What was before the Big Bang? Why the universe is so uniform? Why it is not exactly uniform? Because we need some non-uniformities to create galaxies. Why it is isotropic means the same in all directions. Why all of its parts started expanding simultaneously. Why it is practically flat, not closed, not open, but with a very large accuracy. It's flat, which in cosmological language means some parameter omega equal 1. Well, so all of these questions. And for the first one, we still do not know the full answer, but we are coming closer and we have some ideas based on quantum cosmology. And all other questions would have some possible answer with the contents of inflationary cosmology. So the basic idea of inflation. Now, do not take the box with 1000 protons. Instead, take the box with a heavy vacuum. And this sounds very strange. What does it mean, heavy vacuum? Well, just not far long ago, approximately 27 years ago, we found that empty space in the universe is not exactly empty. It has some non-zero vacuum energy called cosmological constant. So vacuum may have energy, and in fact, this is a part of the modern theory of elementary particle physics. It may have energy first stored in itself, and then depending on some fields which exist in the universe. The most famous one is Higgs field, and there is a Higgs effect, which is the basis of electroweak theory. So you may have energy stored in the vacuum. And when you think about vacuum, this is something which is characterized by energy density of the universe. So when the universe expands, energy density of empty space remains the same. Nothing changes. It's the same empty. So the energy density remains the same, but the total energy is proportional to volume. And therefore, if this picture makes any sense, then interestingly, the total energy of the universe will continue growing and growing and growing just by, well, letting universe with a heavy vacuum expand. So this look something wrong. It couldn't be so. But the situation is rather tricky, and it actually happens quite consistent with known laws of elementary particle physics. Energy for the whole universe, including gravitational energy, is conserved, but energy of matter is not. You have a balance between gravitational energy and energy of matter. And if you have this configuration, which I've shown you, the total energy of matter can grow, and it will be proportional to the total volume. So the larger is the universe, the more energy it has, the matter energy of the universe. Basic idea can be illustrated by describing this vacuum expanding in the expanding universe. And that's the first simplest equation, which is Hubble equation, showing that the speed of expansion is proportional to, here I have a typo. The speed of expansion is proportional not to not to potential energy squared. It is proportional to energy. So I will need to erase this factor 2 there. It has a solution which describes the universe growing exponentially. It just, you solve equations in general theory of relativity. You have this answer. There is nothing special about it. And then total energy of the universe is growing exponentially, because if size of the universe grows exponentially, then the total energy is volume, grows like volume, so it goes three times faster. And that was the basic idea of inflationary theory proposed by Alan Guth in 1980. And that was great idea, absolutely. But then if something looks too good to be true, that sometimes it is too good to be true. If the universe is empty, how can anyone know that it expands? The universe with a constant vacuum energy is described in general theory of relativity as de Sitter space. And for de Sitter space, it is known some paradoxical thing that in one coordinate system it expands, in another coordinate system it collapses, and another coordinate system is static because it's vacuum and there is no way in vacuum to define what is expansion. So there is no preferable coordinate system. And as a result of that, when this vacuum starts decaying to produce normal matter, then this decay happens very inhomogeneously, and the universe becomes very, very bad, very inhomogeneous. So after about a year of investigation, Guth, as well as Hawking with their collaborators, concluded that the theory cannot be improved and does not work as it is. But fortunately, it was possible to break some of the assumptions of the original theory. And instead of vacuum, which stays with constant vacuum energy, one should consider scalar field, which slowly changes in time. And this slow change is very important in gradient of the theory. So if we do it, it's possible to avoid this objection which I just gave you. And the simplest scenario, which was already mentioned in the introduction, is the so-called theory of chaotic inflation. That's the simplest version of it. You have a theory where a scalar field, which exists everywhere in the universe, you will consider it in a tiny speck of space in the universe and assume that it is more or less homogeneous and slowly moving. The first line is Lagrangian describing this universe. So if you study the theory, the first term is R, is gravity, the second term is kinetic and gradient energy of scalar field, and the third one is potential energy. So if you let the scalar field evolve, it does not want to have any non-zero value. Its potential energy is similar to this curve, which is written here in this picture. And the scalar field looks like a ball here. So if you start with scalar field having very large magnitude, it wants to go slowly down. But it goes down slowly because of some magic of equations here. This second equation describes the motion of the scalar field, and it contains this term 3h phi dot, which in normal mechanics called friction term. If you study harmonic oscillator, its equation will be exactly like that. Phi 2 dots is equal to minus m squared phi. That's equation for harmonic oscillator. The second term is friction term. And this friction term tells you that if Hubble constant, which stays here like a friction coefficient, if Hubble constant large, then the scalar field moves down very, very slowly. And therefore, during a long time, scalar field stays approximately the same height. If it stays at approximately the same height, then the analysis which we made before using these equations is approximately valid. Energy of a scalar field is approximately constant, then expansion of the universe is approximately exponential. And that was the basic idea. And you solve these equations exactly already for the scalar field phi, and use this analogy with harmonic oscillator, analyze it, but you solve this equation exactly. And what you find is that the universe expands approximately exponentially and become very large very quickly. So you may start with the whole universe occupying only the having size 10 to the minus 33 centimeter, which is Planckian length. You cannot go smaller than that because you will be unable to describe it in terms of normal physics. And at that time, energy may be smaller than a mass, smaller than a milligram, and then you wait very small time, approximately 10 to the minus 30 seconds, and the universe becomes as big in any units of length. And if you have here any mountains, any inhomogeneities on the universe, then they are stretched, the universe becomes uniform, and all the problems which bothered us before, they disappear, they are solved. So where are the particles? If you have no particles, there are only scalar field, and then it becomes huge. These elementary particles were created by the decay of the scalar field, and it happens gradually in all different parts of the universe, and there is no, well, collisions of the walls of the bubble, which was a property of a theory of Alan Guth. So the universe becomes almost uniform. But almost uniform is not a good thing, because you need to have not just a spherically symmetric ball which is totally uniform, you need to have some inhomogeneities which give rise to galaxies. And here quantum mechanics helps. And that was the following. In vacuum, even right now, we're surrounded by quantum fluctuations. And in an expanding universe, these quantum fluctuations, they grow in their wavelengths. And then universe continue expanding and they grow, and eventually they overlap with each other and form this slightly inhomogeneous background. The theory of this was developed for the first time by Mukhanov and Chibisov in Russia, and I was at that time also working there in the nearby office, and I told them, well, but this does not make any sense, because you are saying that galaxies have been formed by quantum fluctuations. This cannot be right. And then I tried to understand, and yes, that was brilliant idea. And that actually, right now, this is the only mechanism which accepted by everybody, the theory of formation of large-scale structure of the universe created by quantum fluctuations. So this will be important part of understanding of what this multiverse is about. Quantum fluctuations can form large-scale structure of our universe. When I am talking about inflation, you may say, oh, but who knows? It's like science fiction. Nobody was there to observe the universe. How we really know that this theory is accurate? Well, first of all, this is at the moment the only theory that I know which was demonstrably, people came and checked and checked and checked that the equations are right, the derivations are correct. The only theory which we know that can explain why the universe is large, why it is isotropic, why it is uniform. It also predicts that the perturbations produced by inflation are of a special kind, adiabatic, and that's exactly what was found experimentally. They also show that perturbations have some special peaks in the spectrum, and the peaks of the spectrum were observed. They show that the two different types of perturbations which exist there, they must have some anti-correlations, and that was also something observed. Then inflationary perturbations were predicted to have practically flat spectrum, do not the spectrum which does not depend on the logarithm of distance, and that was also confirmed, and many other things which I mentioned here, something about non-Gaussianity. So about 10 different pieces of evidence in favor of inflationary cosmology. So let's assume that this is the theory which describes our world. In particular, this was the picture obtained by Planck satellite about 10 years ago, which shows perturbations, tiny perturbations of temperature of sky, which we look around right now. It's really, really tiny at the level of like 1 divided by 10,000 of temperature of the microwave background radiation. It was possible to find all of these small things. And this is essentially a photograph, a photographic image on the scale of all observable part of the universe of results of quantum fluctuations at the birth of the universe. So it's really amazing. And there are some ways of making it numerical. I do not have any possibility to go into details to specify, to quantify these predictions and how the observation check it. For example, some spectrum must have some peaks, and that's exactly what Planck satellite have found. And then it was studied in greater details for different types of perturbations by subsequent experiment, ACT and SPT, and they all confirm the prediction of basic inflationary theories. And it's possible to test it even better if we find out not only this simplest type of quantum fluctuations which was predicted, but also gravitational waves. But spectrum of gravitational amplitude of gravitational waves produced by inflation is expected right now to be much smaller than these simple perturbations studied by Mukhanov and others. So far these are not found, but many people are working on them. It's possible that we will never find it because the amplitude in many theories is so small that whatever we try, we'll never find it. But if we find it, it will be additional 11th evidence in favor of inflationary theory. And that is from a recent paper summarizing experimental status of investigation of inflation in the end of 2025. So just latest paper. Again, if there are any specific questions about details of that, I would be happy to return to it. Right now, it was only to show that people are really doing science about this theory, which originally looked like science fiction, and so far looks so good. And I probably will not discuss the details of the theory. So I will mention you only this. I gave an example of the theory with the simplest potential, m squared, phi squared. The simplest, like a harmonic oscillator. But this simplest theory predicts the spectrum of perturbations, which was already ruled out experimentally because it would predicted to produce too large amplitude of gravitational waves. However, it is sufficient to modify this potential just slightly, add two different terms of polynomial for the potential, make this potential looking like it is right now, and everything will fit present experimental data. Okay, so that was a basis of the theory. Now we are going to something more interesting. Well, this was incredibly interesting when we were discovering all of this, but this was the story of 45 years ago. Now we live with consequences. And the consequence is the following. Uniformity of our universe is explained by inflation. So exponential stretching of the universe makes all parts of the universe looking alike because they originated from the same place. But now, and that will be the important part, that on the larger scale, the universe can be and probably should be 100% non-uniform. And that will be this discussion of the multiverse. Here comes the general idea of why this could be so. Remember, we start with this small red ball and then expanding, and when it expands, the whole universe becomes red, which means that if one or part of the universe had some specific properties, by red, I mean vacuum state of a specific type, then the universe exponentially expands, and this vacuum state expands on the whole universe. When you have laws of physics of a given type operating this red ball, they expand and the universe becomes red everywhere. Everything is similar to what was in the beginning at the expansion of this red ball. But if I start with a football, you have a universe, part of it was red, part of it was white, part of it was blue. And then it blown up by exponential expansion of the universe. And we live, for example, in the blue domain, the blue part of the universe. And in the blue part of the universe, we will look around at the huge distance, we will see only blue. And in the white universe, we'll see only white. By this blue and white, actually, what I mean is that our universe may have some different realizations of laws of physics in different parts, and I will explain it later, okay? And if we look around, we will see surrounded by a part of the universe of certain properties. The people who were born, and whoever was there, who was born in a yellow universe, they will see the universe of this type of properties, and nobody would suspect that somewhere else the properties of the universe would be different, because all our experimental data would be about blue universe if we live there, or about red universe for those who live in this red universe. So then, how do we know that our universe does not have these red and blue and green different areas with different properties? And there are two attitudes to this question. One of them is a pessimist, and a pessimist says that if the multiverse, which is so large and it contains different parts with different properties, is so huge that we never see other parts, then it is impossible to prove that we live in the multiverse. An optimist says, optimist practically repeats what pessimist said. If each part of the universe is huge, we will never see other parts, so it's impossible to disprove that we live in the multiverse. And the Einstein said, I would rather be an optimist and a fool than a pessimist and right. So the whole idea is that the basic theory is that you have a multiplicity of different things. And how can you prove that our universe is everywhere the same? And previously, we had an idea about the universe. Then we have a telescope. You look at the telescope and you see and you look at the whole universe. But in inflationary universe, the size of the universe is billions and billions and billions of times larger than the small parts which we can observe in the telescope. So how do we know what is in the other parts of the universe? And what else happens is that even if we start with the universe of one particular type, quantum fluctuations may divide it into pieces with different types of, well, effectively universes, because for each of us who live in this huge red area or huge blue area, this would look like everything, but we will just be able to see only a small part of it. I think that I better skip into some philosophical discussions here, because I have only 15 minutes, approximately 15 minutes, maybe 20, to a moment when I should finish. I will go directly to some realizations. So this is a technical example. This is the theory which was known to physicists long time ago. In 82, Steven Weinberg, famous physicist who invented standard one model of elementary particle physics, he described something which is called supersymmetric SU5 model. This model has potential energy which have three different minima. In one of them, symmetry, SU5 symmetry between elementary particles is broken. In another, you have a symmetry describing elementary particle theory of a different type, SU4 cross U1. And another one, we have symmetry which just describe the science which we observe around us. Okay? And he asked the question, how can we come? Why we are not in a more symmetric minimum? Why we are in this SU3 cross U2 cross U1, which is necessary for having strong, this is SU3, weak and electromagnetic interactions, which is these two groups, SU2 and U1. And he studied thermal beginning hot Big Bang universe and found that in the beginning only SU5 minimum existed. So how we will be able to jump to this SU3 minimum if in the beginning it was only SU5 and then gradually this one appears, but what would force us to come from SU5 to the part of the universe of our type? And I found the possible answer. During inflation, these quantum fluctuations bring us to all of these minima of the potential, SU5, SU4, SU3, and therefore in our huge multiverse, you will have parts of the universe where this symmetry SU5 is unbroken, and there is no difference between leptons and baryons in this universe, and we cannot live there. In some parts of the universe, you have physics of this type, SU4, and in some of parts of the universe, you have this SU3 cross U2 cross U1, and we can live there. So no surprise that we live in a part of the universe where we can live. We cannot live in the red, we cannot live in the dark blue, we can live in these green ones. The only problem is how you create them. And so we make computer simulations of quantum fluctuations in this theory. And you start with the universe, which was in the beginning red, and then quantum fluctuations change it. By what I mean by red, etc. Remember, I have shown you minima. One minima we painted red. So if you are in SU5, you show the universe red color. If you are in this minimum, blue. If you are green, then this is what we want. And you start quantum fluctuations, you run, and you see how you start with red, and then quantum fluctuations divide the universe in different parts. Universe at that time continue growing and growing exponentially, and it continued this process of division into different regions. Scalar field jumps from red minimum to blue minimum to red minimum back to green minimum, and then gradually this kind of stabilizes. Process ends. The field stops jumping. It lays down an expanding universe in one of the minima, and we live in one of these minima. And this is the end story. You have some parts of the universe where it is blue, and we cannot live there. Some parts of the universe where it is red, and we cannot live there. And some parts where green, and we can live there. That's the main idea of the universe, multiverse. This particular version of the universe is just very similar to what we have on Earth right now. You have on Earth where you have different countries. You have China, you have Russia, you have United States, you have India, and each of these countries have their laws operating on each of them. So you have a universe which is expected to be much larger than people thought before there is, and it is divided into different countries, if you wish. One country with this blue law of physics, SU4 cross U1, another is red, SU5, and another is green, and this is our physics. And we can live only in the parts where we can live. So we learned an interesting lesson. Okay. Alan Guth in 81 said, it is said that there is no such thing as a free lunch, but the universe is the ultimate free lunch. And that was something which he said a long, long time ago to illustrate that what happens. You have practically nothing in the beginning, and then you have everything. How is that? It's free universe with all of these 10 to the 90 particles and more produced from practically nothing. And then next step was when I said, now the universe is not just a free lunch, it's eternal feast where all possible type of dishes, green, blue, orange, whatever types of whatever is possible are served. We have different vacuum states in different parts of the universe. But at that time, it looks like, well, science fiction. I've said it, I've written it in some proceedings. Nobody cared because it's a bit too abstract to think about things like that. This whole thing is science fiction. Gradually, people start understanding that this is not really science fiction. But if it would work, this would be magic, because we would be able to justify the entropic principle, explaining that we live in those parts of the multiverse where we can live. Now, what changed lately, starting from 2003, in 2003, at Stanford, together with Kachero, Kalash, Trivedi, which was well, a very talented physicist from India, and we developed something which is called KKLT mechanism in the name of the authors, which explains how to stabilize vacuum in string theory. It is extremely complicated theory. I was there mostly like a cosmology consultant. It was studying tunneling from one vacuum to another. But what we have studied there, if this string theory of this type is correct, and people are still debating it, there is no statement that this is the truth, absolutely. But this is come as close to truth as we can check at the moment, at least some possible realization of it. So what we have found, and other people have found the number of different vacuum string theory. We have found a way to stabilize vacuum in string theory. And vacuum in string theory depends on, in string theory, you start with 10 dimensions, but 6 of them are compactified, and 4 remains, and 3 of them are space, and 1 time. So why 6 dimensions are compactified? And could they be compactified differently? What if only 2 of them are compactified? How many different options, different possibilities to do so? And what fields live in these different dimensions depending on different types of compactifications? And then when they estimated, they found 10 to the degree 500. That's not 1 billion, that's not 100 billion, that's not 100 billion, that's not even a Google. This is much greater number. And then they start calculating, maybe we made some mistaken estimates, and then they start talking about no, maybe it's not 10 to the degree 500, maybe it's 10 to the degree 1500. So then now some people say, no, it all is impossible and everything is different. Well, we do not know really, but string theory is the best toy model of how the universe may look. So it is a very serious thing. And so many string theorists took these results very seriously, and they start then thinking, so what does it mean? If our universe may have not just 3 colors, which I've shown you, universe is green and red and blue, 3 different types of vacua, and each vacuum gives you different laws of particle physics living in this vacuum. So maybe not 3 colors, but it's 10 to the 500 different colors, much more than any of our computers can produce. And then we start checking what is the probability for us to live in the green universe as compared to others. And here I cannot stop. There cannot describe all of this with discussion of probabilities. If you have some questions about it, I will answer. But the basic idea is that, and this is an example of vacuum energy. People did not know why vacuum energy, which was discovered in 1998 by supernova observations, why it is so extraordinarily small. People thought that vacuum energy is just zero because it's vacuum. They found experimentally that this is not zero but extremely small. However, if vacuum energy corresponding to the minima of these potentials, if vacuum energy would be much larger than this tiny volume, then the universe right now would expand too fast and the galaxies would be torn apart. If it would be small but negative, then the universe would collapse and we also would be unable to live. And only when the vacuum energy is exactly in the range which was experimentally discovered, people like us can exist in the universe. So you have strange coincidence. If you think that the universe consists of 10 to the degree 500 different types, then there are many, many vacua where we can live, and we do not care about others where we cannot. Another example, why we live in the universe with 3 dimensions. Well, I spent some like 3 months in the Leiden University in Netherlands, and this university, at each floor, in each corner, you see portraits of Ehrenfest, and here is in the middle here, surrounded by Einstein and Lorentz and others. So nobody there knew that in 1917, Ehrenfest produced an explanation why we live in 3-dimensional universe. Why indeed? Because, of course, why would we have any other choice? In a normal theory, yeah, well, we live in 3-dimensional space. So you open any textbook on physics, you live in 3-dimensional space. What's the question? But in string theory, you live in 10-dimensional space. And then after compactification, some part of it may be compactified, and you will see that it is two-dimensional, and in some parts the universe is five-dimensional. So why we are living in three-dimensional universe? So he gave the solution of this question even before any string theory was invented. He said that if we live in the universe with more than three spatial dimensions, then planetary systems would be unstable and atomic systems would be unstable. If we would live in the universe with two dimensions, space dimensions, or one, then there are no gravity forces at all between different bodies. This is a surprising fact which can be understood only in contents of general theory of relativity. So now we know that if we would have a chance to have universe consisting of different parts with different dimensionality, now we understand that we live in three-dimensional universe. We require planetary system for our type of life. But somebody else who does not need planetary systems, they may live in some other parts of the universe, in six-dimensional, 10-dimensional universe without any compactification. But it's not that we are creating the universe by our desire. It's we're establishing relation between the universe and our part of the universe, its proper ourself and the properties of the universe where we can live. Like dolphins can live in water, and humans can live only in solid land, water only temporarily. So this is just a relation between us and the properties of our part of the universe. No metaphysics here. Can we test the multiverse theory? And that is an important philosophical issue, because I already mentioned to you that different parts of the multiverse may be so enormously large that you cannot ever see these other parts of the universe. So you may often hear somebody say that, yeah, but the theory of the multiverse, you cannot get any experimental confirmation of this theory. Well, in order to analyze this, I will use an authority which was not really of a scientist, but of a great, detective. Sherlock Holmes, of course, it was the person who suggested some basic principle, which actually a very important part of the way how we operate even in science. He said that when you have eliminated impossible, whatever remains, however improbable, must be the truth. So what did we eliminate? What is the truth? For about 100 years, we were trying to find out why the vacuum energy is so small, and maybe why it is exactly zero. And now it's so immensely so small, and we so far, 27 years after the discovery of the small cosmological constant, we have no other way of explaining why it is so small except for using these anthropic considerations. Consider neutron and proton. The mass of the proton and the mass of the neutron differ by less than 1%. Why they are so similar, the different particles, why they are so similar? It's just coincidence. Well, if the proton would be 1% heavier, then all protons would decay into neutrons. And what you will have are only neutron stars, not single person. If neutron would be 1% heavier than the proton, then neutrons would decay to the protons. There would be no different atoms except for atom of hydrogen. Also, we cannot live there. So we say, oh, anthropic principle explains why neutron and proton are so similar to each other. How about the electron? Electron has mass 2,000 times smaller than the mass of the proton and neutron. Why it is so small? Oh, let's think about the part of the universe where electron is, say, 10 times heavier or 10 times lighter. Physics would be different there. We would be unable to live there. How about the charge of the electron? Change it significantly. We also cannot live there. But all of this looks like cheap philosophy. It is like, something unhealthy with this. Anthropic principle, physicists hated it until you have a physical realization of why this anthropic principle may make sense. And for that, we really need a possibility to live in the universe where electrons have different mass and the proton has different mass and the dimensional space have different dimensions than 3. Then suddenly you have a theory which explains all of these puzzles, all of these dramatic coincidences uh, which exist in physics and going well beyond the physics. For that, we need a multiverse. So the multiverse right now is the only uh, framework which allows you to answer to all of these experimental questions. Experimental question, why the cosmological constant is so small. Experimental question, why proton is so similar in mass to neutron, and why electron is so light, and what is the value of its charge. These experimental questions are now now we have a way to examine it and to possibly give an answer in this context. And so far, we do not have any other answer. And then using this principle, when you have eliminated the impossible explanation, so many years we're trying to give an explanation to this experimental fact. And now we have explanation of this experimental fact. And it's only the theory of multiverse gives this explanation. Unfortunately, I'm afraid that this is a time for me to stop, and I would be able to go a little bit longer, maybe just 3 minutes. Can you give me 3 minutes?
Yes, sir, sure. Yes.
Okay. So just to illustrate the strange way of thinking about things which appears right now. Long time ago, Albert Einstein said, the most incomprehensible thing about the universe is that it is comprehensible. How is that? Our universe was well created in the way we can understand it. We have science, we have some, well, mathematics works perfectly well there. So this is a mystery. Then mathematician Eugen Wigner said, the unreasonable efficiency of mathematics in science is a given we never understand nor deserve. So how is that? The most famous physicist does not understand why physics work. The most famous mathematician does not understand why mathematics work. Then famous Russian mathematician living later in the United States, Gelfand, says, there is only one thing which is more unreasonable than unreasonable efficiency of mathematics and physics, and that it is unreasonable ineffectiveness of mathematics and biology. So all of these people were saying something like that. Why? Why is that? Why we're so lucky that we have a theory which can explain our universe? Why the theory? Why it works? And the reason why Einstein was puzzled and Wigner also by efficiency is that if the universe is everywhere the same, no choice, then the fact that it obeys so many different laws that we can discover, remember, and use can be considered as an undeserved gift of God to physicists and mathematicians. Okay, so maybe this is how it worked. But can we have alternative explanation? And the alternative explanation is that in the inflationary multiverse, which you may also say, okay, but this was also created by God. But I'm just saying you that in inflationary multiverse, the laws of mathematics and physics are efficient only if they allow us to make reliable predictions. That means efficient, okay? And this reliability of predictions is necessary for our survival, because this is how the game of fitness appear. We can predict what happened with us. That's why we can well, win in the game of evolution. But this means that we can live only in parts of the universe which allows efficient physics and mathematics, because this is necessary for these calculations to be made and the results of it to be remembered. So we live only in the parts of the universe where mathematics and physics are efficient. That solves the problem which bothered Einstein and Wigner. And this looks like that. This is now, and this is my last slide. This is the way how we can illustrate. This is kind of a sketch, but nevertheless, this is a multiverse. You start with the universe with some type of physics operating in them, and then it starts producing different parts of the universe, and they produce new different parts of the universe, and they were so huge that people living there, they will think, looking at this neck containing, which is at the moment at the place where this bubble emerged, you will see this is the Big Bang, we will say. But this is a Big Bang, this is very big something, but this is not a Big Bang. And where's the Big Bang? Or go back. Okay, so how far go back do I need to go to find the real bang? So this is now the fractal universe, and we can live only in the parts where physics is compatible with our existence. And physicists and mathematicians can live only in the parts of the universe where mathematics is efficient and the universe is comprehensible. And at that, I finish my talk. Thank you very much.
Thank you. Thank you very much, Professor. We are deeply grateful for your profound exploration of the cosmos, which provided our audience with a rigorous analytical framework for understanding the structural complexities of the multiverse. Now, moving forward, a gentle reminder to the audience, you may continue submitting your questions by scanning the QR code displayed on the screen. Alternatively, the Google Form link has been shared in the chat box, so you can ask your questions there. Now let's move to the question answer session. The question, please. Yes, this is a question from Dr. Bharat Pandey from the Government PG College Raniket from India. He's asking, sir, I want to ask if galaxies are ultimately the result of quantum fluctuations, does that mean the universe at its largest scale is rooted in quantum uncertainty? And if so, how does this uncertainty give rise to the precise patterns and uniformity we observe today?
Okay. So here two tricks, one after another. First, we have global expansion of the universe. And imagine that you have Earth, and the radius of the Earth grows exponentially. Then there will be no alpinism in Himalaya, because Himalaya will be stretched, it will be horizontal. And so inflation removes previously existing inhomogeneities. Quantum fluctuations allow to create new inhomogeneities on the top of already homogeneous universe produced by inflation. So if these quantum fluctuations are not very large, then they produce small perturbations which later grow, and they produce locally galaxies. In one place, one galaxy, another place, one galaxy. This is a result of amplification of quantum fluctuations. Okay, in parts of the universe where these quantum fluctuations were large, then they can bring you from red universe to blue universe. That does not happen at a small scale. This requires very large fluctuations, which are very rare. So we live in the part of the universe where everything of the same type, and the maximal result of that are these local fluctuations of the galaxy type, which we observe right now.
Okay, thank you. Thank you, sir. So let's move to the next question. Yes, this is the question by Mr. Srinjay Paul from University of Kalyani. So in inflationary multiverse models, what defines probabilities if there is no preferred observer? How do we interpret probabilities across different possible universes?
Well, since you asking a question, you yourself is a preferred observer. When the moment when you ask a question, you ask a question, okay, let me look at my hands. Oh, they are made from some materials. Let me study what is a part of these materials. Or they have electrons there and protons there, etc. Or so you learn quite a lot of information before you ask a question about cosmology. So then your questions about whether you live in a red universe or blue universe are already conditioned on some answers to some questions related to you. At this moment, you have created already by your previous knowledge, by the previous study, you have created a base of knowledge which make some questions specified for your part of the universe in which you can live. It would be excellent if we would have a possibility to predict also that you must live the greatest probability of this type of the universe. This is so far not a solved problem, and we do not even know whether this problem whether it can be solved, because somehow we physicists are rooted in the idea of objective reality and everything, and things like consciousness usually do not matter for them, and many other things which are kind of more interesting to the institute where I'm giving a talk right now. But yes, that the questions which you asked are already specify that you live not in the green universe, sorry, not in the red universe where you cannot live, but the green universe. Then you already put yourself firmly in the green universe with these properties of elementary particle physics, actively working there.
Okay, thank you. Thank you so much, sir. So let's move to the next question. This is the question by Professor Tejendra Singh from the Tata Institute of Fundamental Research. So he's asking that in the enormous string theory landscape produced by different compactifications, have we derived one which reproduces our observed universe? Say one that has the low energy fine structure constant is 1 by 137. There are 3 fermion generations, and the muon is 206 times heavier than the electron.
Yeah. Okay. So the answer to this question will be a bit disappointing. On the other hand, it will explain the way people think about it right now. Disappointing in the sense that string theory is immensely complicated. When we start working on this compactification and other things, I was surrounded by 3 wonderful string theorists who were working in this area. There are many outstanding physicists and mathematicians working on this, but string theory is just immensely complicated. We even do not know, honestly, whether this KKLT mechanism or some other mechanism of compactification of the universe, whether they are really achievable or not, simply because of the complexities. So what we did, under certain assumptions, we have this construction, seem to be, at least at the first glance, consistent. What will be the consequences? So other people come and have slightly different version of string theory and have completely different consequences. And the only fact that remains that whatever type of string theory they study, usually, and I mean, if everything works, okay, then the total number of types is combinatorially large. It actually goes back many years back in time to when I visited academician Andrei Sakharov in his exile in Gorky, and Sakharov was a creator of Russian atomic bomb, one of the main leaders there. But he was also outstanding physicist, and he was interested why cosmological constant is so small. And he said, if the and this was before string theory, or at the moment when it started just generating, people start talking about many compactifications. And he say, okay, consider the universe with sufficiently large dimensionality, then combinatorial possibility of topologies which emerge as a result of compactification of sufficiently multidimensional universe is exponentially large. And that explains the number of different possibilities that you study. So if you have 10 to the degree 1000 of different laws of physics, then it is not so surprising if one of them gives you the muon mass exactly as it is, and another gives you top quark mass exactly what it is, and the number of dimensions exactly, because we have right now the total number of options so large that it does not fit your mind. And that is my only way of answering this question.
Okay, thank you. Thank you so much, Professor. Moving to the next question. This is also from Dr. Bharat Pandey from Government PG College, Raniket. So he's asking that Newton gave us universal laws and Einstein refined them for our universe. But in the idea of the multiverse, are these laws truly universal or just local to our universe? Could these exist universes where even gravity or space-time behaves completely differently?
Okay, so the answer is this. Newton considered three-dimensional flat space without any gravitational waves and curvature. We already know that this is not completely right. Einstein make a next step and say that our universe can be curved. And in some limits, you reproduce the laws of gravity by Newton. But it was still three space dimensions and one time. String theory came and said that we live in a space with 10 dimensions, so 9 dimensions of space, 1 dimension of time. But why we don't feel that this is the case? So we have these different types of compactifications. And once we have different types of compactifications, there could be, as I already mentioned, the universe which is two-dimensional. And in two-dimensional universe, there is no gravitational attraction between far removed bodies. So yes, indeed, that is the main well subject of the talk. That if our theory is general enough, and string theory is just an attempt of a theoretical description, which may be the best which we can do right now. Maybe it's totally the best. Maybe it's just the same beginning like Newton theory was for Einstein theory. But what it tells you that the total number of possibilities in this theory can be, no guarantee, but can be exponentially large. And then, therefore, realization of different laws of physics in different parts of the universe may be different. It's, if you wish, there may be a fundamental law of physics and like phases, like water can be liquid and solid and gas. It's the same chemistry, the same H2O. But when your ship goes in water and the captain thinks that only water exists, then no surprise that Titanic crash into iceberg. Okay, so we just must be prepared.
Okay, okay, Professor. So we have a few more questions. So would you be comfortable to take a few more questions, sir? Uh, excuse me, sir. So can we take a few more questions, sir? Are you comfortable?
of course.
Okay, okay, thank you. Thank you so much. So this is by Mr. Nikhil. If the effective laws of physics arise from the compactification of extra dimensions in string theory, can we meaningfully think of this compactification data as the genetic code of the universe, analogous to the DNA encoding the biological traits?
Yes, and actually, the first time I've heard this analogy from Leonard Susskind, who have written a book containing this description. Indeed, if you have some uh, original genetic code of the universe, you start with the universe having like electroweak interaction and strong interaction and gravity, and then inflation happen in this kind of universe. Then in some parts of the universe, quantum fluctuations make this universe to bifurcate. You have mutation in the genetic code, and you produce slightly different type of laws of physics, and then there continue mutations continue. Uh, so this analogy is very fruitful. On the other hand, the complexity of the situation and the possibilities which we are encountering right now, they are much more diverse than the simple I'm calling it simple. The simple picture when the universe just grows like a tree and produce you different parts of different colors. This simple possibility is not the only one possible. And I mentioned it in some of the slides, and I didn't even discuss it, that if you believe in quantum cosmology, then any solution, any possibility, which not even the possibility which cannot be created by mutation, because mutation of an elephant produces an ill elephant, but maybe it will still want to produce something similar to elephant and not produce a bug. Okay, so this tree may produce quite a lot, but these basic trees may be different. So in quantum wave function of the universe may uh, contain information about all of these possibilities, even more than what can be produced by bifurcation. And then we come to something even more basic. So what does it mean about these laws of physics and where they have been written if there was no blackboards to write them and people to remember? So, well, the very important questions where the issue of what consciousness is, what the universe is, in some more fundamental level come to game.
Okay, thank you. Thank you, Professor. So we'll take one more question.
Yeah.
This is by Miss Samisha Shaikh from Edify School, Grade 12. Professor Linde, regarding eternal inflation, we often discuss the birth of bubble universes. Is there a physical mechanism within the multiverse framework that allows for collapsing bubbles or regions of local contraction to coexist alongside the global inflationary background?
Yeah. Okay. So the answer is the following. Suppose you have a piece of cheese with bubbles in it. It's like Swiss cheese. Okay. So this is a Swiss cheese universe. And bubbles start growing inside the Swiss cheese. But the piece of Swiss cheese expands faster than bubble grow. Then this bubble will never cover the whole universe. And the other bubbles also. So that's the rather strange situation, which is possible because of general theory of relativity, because of this exponential expansion. That if something happens inside an exponential expanding universe, under certain conditions, not always, but under certain conditions, this tunneling to unstable regions. You can go from exponentially expanding state, then locally you can tunnel to anti-de Sitter space, which immediately collapses and disappears. But this wall of anti-de Sitter, or something collapsing, expands with the speed equal to the speed of light. But the exponentially expanding universe expands faster.
Thank you. Thank you, Professor, for such wonderful answer. So, and I also thank you for addressing all these questions with such depth and clarity. While the volume of insightful inquiries reflects the depth of today's discussion, but we must conclude the session to the respect of our schedule. So, on behalf of Bhaktivedanta Institute and all the audience, I would like to once again express our sincere gratitude to to you for sharing your insights and wisdom with us today. Your lecture has given us deep insights into science and our understanding of the universe, and we are truly grateful for your time and generosity. Thank you very much,
Thank
Professor.
and thank
Thank
you
you.
very much, and thank you for all interesting questions which you asked.
Thank you.
Goodbye.
Thank you. Bye. Bye. So, moving forward to tomorrow's schedule, tomorrow we have a lineup of world-renowned speakers, and we warmly invite all of you to continue joining us for these fascinating sessions. At 5 p.m., we are honored to host Professor Offer Lau, Department of Physics and Astronomy, University College London, UK. He will speak on Is Dark Energy Evolving with Cosmic Time? And then at 6 p.m., we have a wonderful talk by Professor Tim Eastman. He's formerly from University of Alaska, USA. He will speak on plasma cosmology. At 7 p.m. IST, we will hear from Professor George Ellis from Department of Mathematics, University of Cape Town. So please do join us for these inspiring lectures from some of the greatest minds in the cosmology. We look forward to your continued participation. So let me introduce you a breathtaking work, Quantum Physics and Consciousness. This volume offers a rare, intimate glimpse into the foundational thoughts of the giants of the 20th century science, including Max Planck, Niels Bohr, and Werner Heisenberg. This collection focuses on the fascinating moment in history when the discovery of quantum mechanics has begun to reshape our understanding of the physical world, exploring how these Nobel laureates, Professor Wigner and Professor Anthony Leggett, navigated the profound scientific implications of their own revolutionary research. You are welcome to discover more about this research by visiting our online collection at store.bingstud.org. It's my honor to introduce you Tattva Jigyasa, magazine from the Bhaktivedanta Institute, which examines foundational questions at the intersection of physics, cosmology, and the other fascinating areas. This issue features contributions from Dr. Robert Ma, Senior Research Scientist at NASA, and Dr. Bernard Hash, astrophysicist from the University of California, examining cosmological questions concerning the structure, origin, and underlying order of the universe. We warmly invite you to explore these articles and many more in this stimulating volume. To learn more or to obtain a copy, please visit store.bingstu.org. Once again, I would like to remind about the timing of the lecture series, which will be from 5 p.m. to 8 p.m. from Monday to Friday and 10 a.m. to 1 p.m. on Saturday and Sunday in Indian Standard Time. Once again, we extend our gratitude to all our speakers, the dignitaries, guests, and all our participants for joining us today. Thank you.